You've been arrested for murdering time itself. The detective slides you a photo of time's corpse, which is somehow moving both backward and forward at once. Explain this, he demands. The accusation is absurd, but the question cuts to the heart of one of physics' most perplexing mysteries: the cosmological arrow of time. In 1876, Ludwig Boltzmann proposed his H theorem, suggesting that the universe naturally tends towards states of higher entropy, essentially greater disorder. Yet this seemingly straightforward principle spawned a paradox that still haunts physics today. Consider your morning coffee. The hot liquid cools to room temperature, cream spreads through the black coffee until perfectly mixed, and sugar dissolves completely. We never observe these processes happening in reverse. A cold, mixed coffee spontaneously separating into hot black coffee, cream, and sugar crystals. But here's the thing. Nothing in our fundamental physics equations prevents this reverse process from occurring. The laws of physics work perfectly well in either direction. This one-way flow of time, known as the cosmological arrow, emerges from what physicists call the past hypothesis, the idea that the early universe began in an extremely low entropy state. Roger Penrose's 1979 paper, Singularities and Time Asymmetry, explored this concept in depth, calculating that the odds of our universe starting in such an ordered state by chance were astronomically low, 1 in 10 to the power of 10 to the power of 123, a number so vast it defies comprehension. Think of the universe as an enormous game of snooker. Break the rack, and the balls scatter across the table in increasingly chaotic patterns. You could theoretically reverse each ball's velocity vector precisely, causing them to reform the perfect triangle. But the slightest imperfection in your reverse break would send the system careening toward disorder again. Our universe works similarly. The fundamental asymmetry between past and future emerges from this initial cosmic break. The implications extend far beyond physics. Our very consciousness seems intrinsically linked to this temporal arrow. We remember the past, but not the future. We can affect the future, but not the past. The philosopher Hugh Price's 1996 work, Time's Arrow and Archimedes' Point, argues that this psychological arrow of time fundamentally shapes how we understand causality and free will. What's particularly fascinating is how this microscopic arrow of time connects to the largest scales of cosmic structure. As the universe expands, it creates pockets of order within the overall march toward entropy. Stars form, galaxies coalesce, and complex structures like planets and living beings emerge. Local decreases in entropy that are more than compensated for by the increasing entropy of the universe as a whole. The detective is still waiting for your answer. You explain that you couldn't have killed time because time isn't really a thing at all. It's an emergent property arising from the universe's inexorable movement from order to chaos. The cosmological arrow points the way, but time itself is more like a shadow cast by entropy's relentless increase. Besides, you point out, if you had killed time, wouldn't your alibi and the murder itself be simultaneous? The detective's coffee grows cold as he considers this. You watch the cream swirl through it, creating patterns that will never spontaneously unmix, marking time's passage as surely as any clock. Time's arrow flies on, and you're free to go. Though in a universe of perfect temporal symmetry, perhaps you're also simultaneously arriving at the station, about to be accused of this most peculiar murder. The Zero Theorem. You're standing in an infinitely long hotel with an infinite number of rooms, all of them occupied, when suddenly an infinite bus full of new guests pulls up outside. The hotel manager doesn't panic. She simply asks each current guest to move to the room number that's double their current room number. Room 1 moves to 2, 2 moves to 4, 3 moves to 6, and so on. Now all the odd-numbered rooms are empty, ready for the infinite new arrivals. But here's where things get properly strange. Even after accommodating these infinite new guests, the hotel isn't any more full than it was before. Both scenarios contain exactly the same amount of infinity. This famous thought experiment, known as Hilbert's Hotel, introduces us to one of mathematics' most perplexing concepts, the Zero Theorem. Developed by mathematician Georg Cantor in the late 19th century, the Zero Theorem demonstrates that 1 plus negative 1 plus 1 plus negative 1 plus 1, continuing infinitely, could somehow equal 1/2. Not 0, as our intuition might suggest, but 1/2. The mathematics behind this seemingly impossible result involves what we call divergent series, sequences of numbers that don't settle down to a specific sum. In 1735, Leonhard Euler first grappled with these troublesome series, recognizing that our normal rules of arithmetic break down when we venture into infinite territory. The Zero Theorem emerged from this mathematical wilderness, challenging our fundamental understanding of addition and subtraction. But the implications run far deeper than mere arithmetic. When physicists Richard Feynman and Julian Schwinger were developing quantum electrodynamics in the 1940s, they encountered similar infinite series in their calculations. The mathematics seemed to suggest that the electron's mass and charge were actually infinite, a clearly nonsensical result, given that we can measure these properties quite precisely. The solution they developed, called renormalization, uses a technique remarkably similar to the logic of the Zero Theorem. By carefully grouping terms and applying specific rules about how to handle infinities, they managed to extract finite, physically meaningful results from their calculations. This approach proved so successful that it became a cornerstone of modern quantum field theory. The Zero Theorem's influence extends into modern string theory, where similar mathematical techniques help physicists make sense of the extra dimensions their equations predict. When we try to calculate the energy of vacuum space using quantum field theory, we get an infinite result, unless we apply these special mathematical rules for handling infinities. But there's something profoundly unsettling about all this. We're essentially saying that infinity minus infinity can equal any number we want, depending on how we choose to group our terms. It's as if mathematics itself becomes malleable once we venture beyond the finite realm. This leads to a deeper philosophical question. Are we discovering genuine mathematical truths, or merely inventing convenient rules to make our calculations work? The philosopher Immanuel Kant might have seen the Zero Theorem as evidence for his view that mathematics is synthetic a priori knowledge, something we construct rather than discover. After all, how can we claim to be discovering absolute truth when our results depend on our chosen mathematical conventions? Yet there's another way to look at it. Perhaps the Zero Theorem reveals something fundamental about the nature of infinity itself. Just as quantum mechanics shows us that the microscopic world operates by different rules than our everyday experience, maybe infinity simply doesn't behave the way our finite minds expect it to. The British mathematician G.H. Hardy once wrote that mathematical reality lies outside us, and our function is to discover or observe it. From this perspective, the Zero Theorem isn't a convenient fiction, but a window into a mathematical reality that transcends our intuitive understanding. Back in our infinite hotel, something remarkable happens when you try to count the guests. If you count only the even-numbered rooms, you get infinity. Count only the odd-numbered rooms, you also get infinity. Count all the rooms together, still infinity. The Zero Theorem tells us that these infinities can be manipulated, subdivided, and rearranged in ways that defy common sense, but follow their own rigorous logic. And perhaps that's the most profound lesson of the Zero Theorem. In pushing mathematics to its limits, we discover that reality, whether mathematical, physical, or philosophical, often transcends our intuitive understanding. Just as quantum mechanics forces us to accept wave-particle duality, the Zero Theorem compels us to embrace a mathematics where infinity minus infinity might equal 1/2. And an infinite hotel can always accommodate more guests. The next time you're lying awake pondering the nature of infinity, remember, the truly remarkable thing isn't that these mathematical results seem impossible, it's that they work so. The observer chain. You're peacefully reading a book when suddenly you notice someone watching you through your window. The moment you look up, they quickly turn away, but now someone else is watching them from across the street. That observer is being watched by another person from a balcony, who in turn is being observed by someone in a helicopter, who's being monitored by a satellite, which is being tracked by a space station, and so on, stretching up into the cosmos in an infinite regression of observers. Each one exists solely to watch the previous observer in the chain. It's absurd, yet this peculiar thought experiment illuminates one of quantum mechanics' most profound puzzles, the measurement problem. The concept of observation in quantum mechanics emerged from a series of groundbreaking experiments in the early 20th century, most notably the double-slit experiment first performed by Thomas Young in 1801, but whose quantum implications weren't fully appreciated until the 1920s. In this experiment, individual particles seemed to exist in multiple states simultaneously until they were measured, at which point they would collapse into a definite state. This led to the Copenhagen interpretation of quantum mechanics, proposed by Niels Bohr and Werner Heisenberg in 1927. The Copenhagen interpretation suggests that quantum systems remain in a superposition of states until they interact with a classical measuring device. But this raises an immediate question. What exactly constitutes a measurement? If a detector observes a particle, who or what observes the detector? This is where our infinite chain of observers becomes relevant. John von Neumann formalized this problem in his 1932 book, Mathematical Foundations of Quantum Mechanics. He demonstrated that if you treat the measuring device itself as a quantum system, it too should exist in a superposition until it's observed. But then what observes the observer? This leads to what's known as von Neumann's chain, an infinite regression of observers, each needed to collapse the quantum state of the previous observer. The implications are staggering. If we follow this logic, we need an infinite series of measurements to actually get a definite result. It's rather like trying to support the Earth on the back of a turtle, only to realize that turtle needs to stand on another turtle, leading to the famous quip about it being turtles all the way down. In our case, it's observers all the way up. This observer chain paradox has led to various proposed solutions. Eugene Wigner suggested in 1961 that consciousness itself might be the final observer, effectively terminating the chain. This became known as the Wigner's friend thought experiment, where he proposed that perhaps only conscious observation could collapse quantum states. However, this interpretation raises its own philosophical problems about the nature of consciousness and its role in physical reality. Another approach came from Hugh Everett III in 1957 with his many worlds interpretation. This theory suggests that no collapse occurs at all. Instead, every possible outcome exists in its own branch of reality. In this view, our observer chain isn't actually collapsing anything. It's simply becoming entangled with different branches of a universal wave function. The decoherence theory, developed in the 1970s by H. Dieter Zeh and further refined by Wojciech Zurek, offers a more practical resolution. It suggests that interaction with the environment causes quantum superpositions to effectively collapse through a process called quantum decoherence. This approach doesn't require conscious observers or infinite chains. The environment itself acts as an observer. Modern experiments continue to probe these questions. In 2019, researchers at Heriot-Watt University in Edinburgh conducted an experiment testing quantum entanglement between multiple observers, adding new complexity to our understanding of the measurement problem. Their results suggested that different observers can indeed experience different realities, though they remain consistent within their own framework. The observer chain paradox reveals something profound about the nature of reality and our place in it. We tend to think of observation as a passive act, like watching a play from the audience. But in quantum mechanics, the act of observation is more like joining the cast. We become part of the performance we're trying to observe. Each observer in our chain isn't just watching, they're participating in the creation of reality itself. As you return to your book, perhaps now aware of the countless potential observers that could be collapsing your own quantum state. Remember that the very act of wondering about these observers makes you part of the chain too. In quantum mechanics, as in life, we can never truly be mere spectators. We're always participants in the grand dance of reality, whether we realize it or not. Mirror matter. You wake up one morning to find that everything in your room has been perfectly reversed, not just flipped like a reflection, but fundamentally inverted at the atomic level. Your alarm clock now ticks counterclockwise, the text in your books reads right to left, and even the sugar molecules in your morning coffee spiral in the opposite direction. As you stumble to the bathroom, heart racing, you realize with horror that your own reflection doesn't match your movements anymore, because you're the one that's been reversed, down to your very atoms. This isn't just a thought experiment from some twisted physicist's imagination. It's a window into one of the most perplexing possibilities in modern physics: the existence of mirror matter, a hypothetical form of matter that would be the perfect atomic reflection of everything we know. And when I say perfect reflection, I mean something far more fundamental than what you see in your bathroom mirror. The story of mirror matter begins in 1956 with a crisis in physics. Two Chinese-American physicists, Tsung-Dao Li and Chen-Ning Yang, proposed that a principle everyone had taken for granted, parity symmetry in weak nuclear interactions, might actually be wrong. Parity symmetry suggested that nature shouldn't care about left or right, much like how a mirror image follows the same physical laws as the original object. When Qiansheng Wu tested this idea in her famous beta decay experiment, she found something shocking. Weak nuclear interactions do prefer one direction over another. The universe, it seemed, had a built-in handedness. This discovery sent ripples through the physics community. If the universe could tell left from right at such a fundamental level, what did that mean for the symmetry of nature itself? Robert Foote and his colleagues at the University of Melbourne took this question to its logical extreme in the 1990s. They proposed that for every particle of ordinary matter, there might exist a mirror image particle, creating an entire shadow world of mirror matter. But mirror matter isn't simply matter reflected in a mirror. It's matter where every particle's internal properties are reversed, like changing every left-handed particle into a right-handed one. A mirror proton would still have the same mass as a regular proton, but its internal quarks would be flipped. Mirror atoms would form mirror molecules, which could theoretically combine into mirror matter versions of everything we see around us. The implications are staggering. If mirror matter exists, it would only interact with ordinary matter through gravity and possibly some very weak forces. It would be invisible to our eyes and pass right through regular matter as if it weren't there. In fact, we could be surrounded by mirror matter right now. Entire mirror planets, mirror stars, even mirror people, and we'd have no way to detect them directly. This brings us to one of the most intriguing applications of mirror matter theory: dark matter. The universe appears to contain far more mass than we can see, about 5 times more. This invisible mass, which we call dark matter, might be composed of mirror matter. It would explain why dark matter interacts so weakly with ordinary matter while still exerting gravitational effects. But the rabbit hole goes deeper. If mirror matter exists, it would have its own mirror chemistry, mirror biology, and mirror electromagnetic forces. A mirror matter planet wouldn't just be a reversed version of Earth. It would be built from fundamentally different building blocks, following their own parallel set of physical laws. The mirror life that might evolve there would be entirely alien to us, invisible and untouchable, yet potentially existing right alongside us. The search for mirror matter continues in laboratories around the world. Scientists look for tiny anomalies in particle experiments that might indicate interactions with mirror particles. They search for unusual gravitational effects that could suggest the presence of mirror matter objects. So far, no concrete evidence has been found, but the possibility remains tantalizing. As you sit here, contemplating this bizarre corner of physics, consider that there might be a mirror version of you made of mirror atoms, reading about regular matter and wondering if it exists. Their coffee would spiral in the opposite direction. Their heart would beat on the other side of their chest, and their very atoms would be perfect mirror images of yours. And yet, despite existing in the same space, you would never meet, never interact, forever separated by the fundamental nature of reality itself. Perhaps the most profound aspect of mirror matter isn't its physical implications, but what it tells us about the nature of symmetry in our universe. In a reality where even the most basic particles show a preference for left or right, the existence of mirror matter would restore a kind of cosmic balance. It suggests that perhaps the universe does maintain perfect symmetry after all, just not in the way we originally thought. Quantum coherence. You're falling through an endless series of identical rooms, each containing nothing but a single lit candle. As you pass through each room, you notice something impossible. The candle light in every room flickers in perfect synchronization, as if all the flames are somehow connected across space. This synchronized dance of light isn't just beautiful, it's a glimpse into one of the most bewildering phenomena in quantum physics, quantum coherence. The story of quantum coherence begins in 1924 when Satyendra Nath Bose sent Albert Einstein a paper describing how light particles could occupy the same quantum state. Einstein immediately recognized the profound implications and expanded on Bose's work, leading to the prediction of a new state of matter, the Bose-Einstein condensate. But it would take another 70 years before scientists could create this state in a laboratory. When atoms are cooled to temperatures just billionths of a degree above absolute zero, they begin to lose their individual identities. Rather than behaving as separate particles, they merge into a single quantum entity, much like those synchronized candle flames. This quantum coherent state isn't just a theoretical curiosity, it's fundamentally different from anything we experience in our everyday world. In our normal experience, objects are distinctly separate. A book on your desk is clearly different from another book next to it. But in a quantum coherent system, particles become fundamentally indistinguishable. They don't just look or act the same. They become the same thing, sharing a single quantum state across space. The mathematics behind this is rather elegant, if utterly counterintuitive. The wave functions of the particles, mathematical descriptions of their quantum states, overlap and combine into a single wave function. It's as if the particles are humming the same note in perfect harmony, creating a quantum symphony that extends across space. This phenomenon has profound implications that extend far beyond physics laboratories. Take photosynthesis, for instance. For years, scientists assumed plants captured sunlight through straightforward chemical processes. But research from UC Berkeley in 2007 revealed that quantum coherence plays a crucial role. The light-harvesting molecules in plants maintain quantum coherent states for surprisingly long periods, allowing them to explore multiple energy pathways simultaneously and choose the most efficient route. The implications don't stop there. Our own consciousness might depend on quantum coherent processes in our brains. Sir Roger Penrose and Stuart Hameroff proposed that microtubules, tiny structures within our neurons, maintain quantum coherent states that could be fundamental to consciousness itself. While this remains controversial, it highlights how quantum coherence might be essential to life itself. But perhaps the most practical application lies in quantum computing. Traditional computers process information through bits that are either 0 or 1. Quantum computers use quantum bits, or qubits, that can exist in multiple states simultaneously thanks to quantum coherence. This allows them to perform certain calculations exponentially faster than classical computers. The challenge lies in maintaining these delicate quantum states. Even tiny interactions with the environment can destroy quantum coherence, a process called decoherence. It's like trying to keep those candle flames synchronized while a breeze blows through the room. This is why quantum computers need to be kept at extremely low temperatures and isolated from external disturbances. Yet nature seems to have solved this problem. The quantum coherent states in photosynthetic systems remains stable at room temperature, surrounded by the chaos of cellular activity. This has led to a new field of quantum biology, exploring how living systems harness quantum effects in warm, wet, and noisy environments. The deeper we look into quantum coherence, the more we find it challenging our fundamental understanding of reality. The boundary between the quantum and classical worlds becomes increasingly blurry. Those synchronized candle flames aren't just a metaphor. They're a reminder that at the deepest level, separation might be an illusion. As you continue falling through those endless rooms, watching the perfectly synchronized flames, you might wonder, are we all just parts of a larger quantum coherent system, momentarily decoherent, but fundamentally connected? The answer might lie in those flickering flames, dancing together in perfect quantum harmony. The Unruh Effect. You're having a particularly awful day at the office, sprinting between meetings while trying to avoid your supervisor who's hunting you down about those reports you haven't finished. As you accelerate through the hallways, darting around corners and ducking into conference rooms, you begin to notice something peculiar. The air around you seems to be getting warmer. The faster you run, the hotter it becomes, until the office space itself appears to be glowing with a faint thermal radiation. Congratulations! You've just stumbled upon one of physics' most mind-bending predictions, the Unruh Effect. In 1976, Canadian physicist William Unruh made a remarkable theoretical discovery that would challenge our fundamental understanding of empty space. He mathematically demonstrated that an accelerating observer would experience what appears to be a warm bath of particles and radiation in what an unaccelerated observer would consider to be completely empty space. More precisely, an accelerating observer would detect a thermal spectrum of particles with a temperature proportional to their acceleration. The mathematics behind this effect emerged from Unruh's work combining quantum field theory with special relativity, building upon earlier insights from Stephen Hawking's studies of black hole radiation. The formula itself is deceptively simple. The temperature experienced by the accelerating observer is equal to their acceleration multiplied by h bar, reduced Planck's constant, divided by 2 pi c kb, where c is the speed of light and kb is Boltzmann's constant. The implications, however, are anything but simple. To understand why this happens, we need to grapple with the quantum nature of vacuum. In quantum field theory, empty space isn't really empty at all. It's a roiling sea of virtual particles popping in and out of existence, like a cosmic foam of possibility. These virtual particles typically appear in pairs that almost immediately annihilate each other, making them undetectable to stationary observers. However, when you accelerate through space, you change your reference frame in such a way that these quantum fluctuations appear to take on a different character. Think of it like trying to listen to a conversation while running past the speakers. The Doppler effect causes the sound waves to compress in front of you and stretch behind you, changing their frequency. The Unruh effect works similarly, but with quantum fields instead of sound waves. Your acceleration causes you to perceive the quantum vacuum fluctuations as real thermal radiation, with a temperature that increases the faster you accelerate. The effect is maddeningly subtle in everyday life. To experience a temperature of just 1 Kelvin, you would need to accelerate at about 10 to the power of 21 meters per second squared. That's roughly 100 billion times the acceleration you'd experience in a Formula One car. This is why we haven't directly observed the Unruh effect, despite its solid theoretical foundation in quantum field theory. However, recent proposals involving circular acceleration and quantum circuits might finally allow us to detect this elusive phenomenon. But the implications of the Unruh effect extend far beyond just being an interesting curiosity. It suggests something profound about the nature of reality itself, that the very concept of particles and empty space depends on how you're moving. What one observer considers to be a perfect vacuum, another observer might experience as a warm bath of particles. This relates closely to the phenomenon of Hawking radiation from black holes, where the intense gravitational acceleration near the event horizon causes the vacuum to appear to emit thermal radiation. The effect also raises fascinating philosophical questions about the nature of observation and reality. If two observers in different states of acceleration disagree about the number of particles present in a region of space, which observer is correct? The answer, surprisingly, is both of them. Their different observations are equally valid descriptions of reality from their respective reference frames, much like how Einstein's special relativity showed us that different observers can disagree about simultaneous events while both being correct from their own perspective. So the next time you're racing through your day, accelerating from one task to another, consider the bizarre quantum truth that your very motion through space might be creating a subtle warmth in the vacuum around you. Not that you'd ever be able to notice it, of course, unless you somehow manage to accelerate fast enough to heat your surroundings to the temperature of a cup of tea. Though by that point, I suspect those unfinished reports would be the least of your worries. Quantum Zeno Effect. You're staring at a pot of water, waiting for it to boil. Every few seconds, you lift the lid to check if bubbles have formed yet. Somehow, impossibly, the water seems to take longer to boil than when you leave it alone. You might dismiss this as mere impatience, but you've stumbled upon something profound, a peculiar quantum mechanical phenomenon that suggests reality itself behaves differently when observed. This is the Quantum Zeno Effect, named after the ancient Greek philosopher Zeno of Elea, and it reveals one of the strangest aspects of quantum mechanics. Measurement itself can freeze time. The effect was first formally described in 1977 by physicists E.C.G. Sudarshan and Baidyanath Misra at the University of Texas at Austin. Their paper, The Zeno's Paradox in Quantum Theory, demonstrated mathematically that an unstable particle, if observed continuously, would never decay. It's rather like Zeno's famous paradox about the arrow that can never reach its target because it must first travel half the remaining distance, then half of that, and so on indefinitely. But while Zeno's paradox was a philosophical thought experiment, the quantum Zeno effect is very real, confirmed in numerous laboratory experiments since the 1980s. The key to understanding this bizarre phenomenon lies in one of quantum mechanics' most fundamental principles. The act of measurement forces a quantum system to choose a definite state. In between measurements, quantum systems exist in a superposition of states, rather like Schrödinger's unfortunate cat being simultaneously alive and dead. But when we measure the system, this superposition collapses into a single, definite state. If we measure frequently enough, we effectively freeze the system in its initial state, preventing it from evolving naturally. Think of it like trying to watch a mime perform. Every time you blink, the mime freezes in place, afraid of being caught in motion. The more frequently you blink, the less the mime appears to move at all. In quantum systems, our measurements are like these blinks, forcing the system to repeatedly freeze in its current state. This isn't just a clever analogy. It's been demonstrated in real experiments. In 1989, David Wineland and his team at NIST used the effect to suppress quantum jumps in trapped ions, effectively forcing atoms to remain in their excited states far longer than they naturally would. But the implications of the quantum Zeno effect extend far beyond laboratory curiosities. It raises profound questions about the nature of reality and consciousness. If measurement can freeze quantum processes, and consciousness is ultimately based on quantum processes in our brains, does this suggest that self-awareness might actually be slowing down certain neural processes? Some philosophers and physicists, including Henry Stapp at the University of California, Berkeley, have suggested that the quantum Zeno effect might play a crucial role in how consciousness interacts with the physical brain. The effect also has practical applications. In quantum computing, the quantum Zeno effect can be used to protect quantum states from decoherence, the tendency of quantum systems to lose their quantum properties through interaction with the environment. By repeatedly measuring a quantum bit, qubit, researchers can maintain its quantum state longer, potentially making quantum computers more stable. It's rather like repeatedly checking on a child to make sure they're still in bed. The very act of checking prevents them from getting up to mischief. Of course, like many quantum phenomena, the quantum Zeno effect has a counterintuitive twin, the anti-Zeno effect, discovered in 1997 by Asher Perez. Under certain conditions, frequent measurements can actually accelerate a quantum system's evolution rather than freezing it. It's as if sometimes our watching pot would boil faster precisely because we're watching it. Coming back to that pot of water, while your observations aren't actually triggering the quantum Zeno effect, the system is too large and hot for quantum effects to dominate. You've brushed against a profound truth about the universe. The act of observation isn't passive, it fundamentally changes the reality being observed. Rather like the ancient Greeks who gave us Zeno's paradoxes, we find ourselves confronting deep philosophical questions through the lens of physical phenomena. The only difference is that our modern Zeno effect isn't just philosophy. It's measurable, reproducible, and might just help us build the computers of tomorrow. Biosemiotics. You're reading a book in your garden when a bee lands on a nearby flower. Nothing unusual there, except suddenly you realize you're witnessing one of the most sophisticated communication systems in nature. That bee isn't just randomly visiting flowers. It's participating in a complex dialogue. The flower's vibrant petals are screaming, "I have excellent nectar," in bee vision ultraviolet, while releasing a carefully crafted chemical cocktail that says, "I'm healthy and disease-free." The bee, meanwhile, is reading these signals like a wine connoisseur at a tasting, its tiny brain processing more sensory information than a supercomputer. And here's the truly mind-bending part. Neither the bee nor the flower speaks the same language, yet they're having a conversation that's been refined over millions of years of evolution. This remarkable exchange is just one tiny example of biosemiotics, the study of sign processes and meaningful communication throughout all living systems. The field emerged from the fascinating intersection of biology and semiotics, the study of signs and symbols, primarily through the work of Jakob von Uexküll in the early 20th century. His 1934 work, A Foray into the Worlds of Animals and Humans, introduced the crucial concept of the Umwelt, the unique sensory and meaningful world that each species inhabits. Thomas Sebeok later expanded these ideas at Indiana University, establishing biosemiotics as a distinct field in the 1960s and demonstrating how sign processes are fundamental to all life forms. The implications of biosemiotics are staggering. Every living thing, from bacteria to blue whales, exists in its own semiotic niche, interpreting and responding to signs that might be completely invisible to others. A tick, for example, lives in a world dominated by just 3 signs: the scent of butyric acid, which signals mammal nearby, the temperature of 37 degrees Celsius, which means warm blood, and the sensation of hair, which indicates landing spot. That's it. That's the tick's entire meaningful universe. Yet within this seemingly limited world, it performs complex behaviors that ensure its survival. But biosemiotics goes far deeper than just animal communication. The human body itself is engaged in constant semiotic processes at the cellular level. When you catch a cold, your immune cells aren't just mindlessly attacking invaders. They're engaged in sophisticated sign interpretation. They must recognize specific molecular patterns that signal friend or foe, make decisions based on chemical messages from other cells, and coordinate responses through intricate signaling cascades. The Nobel Prize-winning work of Barbara McClintock in the 1940s and 50s demonstrated that even plant genes engage in complex conversations, responding to stress by moving around the genome in meaningful ways. This leads us to one of the most profound implications of biosemiotics: the challenge it poses to our understanding of consciousness and meaning. If a single cell can interpret signs and make meaningful responses, where exactly do we draw the line between mechanical reaction and genuine interpretation? The work of Jesper Hofmeier at the University of Copenhagen suggests that all living systems are fundamentally semiotic systems. They don't just react to their environment, they interpret it. A tree doesn't just mechanically grow toward light. It interprets light as a sign of good growing direction, based on complex internal processes that have evolved over millions of years. Coming back to our garden scene, that bee and flower are engaged in something far more profound than mere stimulus and response. They're participants in what Hofmeyr calls the semiosphere, the sphere of signs and meanings that permeates all of life, just as the biosphere encompasses all living things. And perhaps most remarkably, we humans, with all our sophisticated language and technology, are just one small part of this vast web of meaning-making that extends from the smallest bacterial colony to the largest ecosystems. Looking at that bee again, you might notice it performing its famous waggle dance back at the hive, a sophisticated symbolic communication that tells other bees the exact distance and direction to that flower you were reading next to. And suddenly you realize, you're not just sitting in a garden. You're immersed in an ocean of meaning, surrounded by countless conversations in languages you never knew existed. The everything formula. You're staring at an equation that theoretically describes every possible event in the universe, from the orbit of electrons to the formation of galaxies, from the flutter of a butterfly's wings to the thoughts forming in your mind as you read these words. It spans across multiple whiteboards, filling the room with a dense forest of mathematical symbols. Your colleague, a theoretical physicist, has just spent 3 hours explaining how this single formula might be the key to understanding literally everything that ever was or will be. There's just one small problem. When you try to actually solve it, the mathematics suggests that nothing should exist at all. This is the Wheeler-DeWitt equation, often called the everything formula or wave function of the universe. First proposed in 1967 by physicists John Wheeler and Bryce DeWitt, it represents perhaps the most ambitious attempt in scientific history to capture the entire universe in a single mathematical expression. The equation emerged from efforts to reconcile quantum mechanics with Einstein's theory of general relativity, two fundamental theories that, rather awkwardly, refuse to play nicely together. The mathematics behind the Wheeler-DeWitt equation builds upon the Schrödinger equation, which describes how quantum systems evolve over time. But while Schrödinger's equation works brilliantly for particles and atoms, Wheeler and DeWitt attempted something far more audacious, applying similar principles to the entire universe itself. The resulting formula is so complex that most physicists need years of specialized training just to understand its basic structure. What makes the everything formula particularly maddening is that it seems to be simultaneously correct and impossible. When you work through its implications, it suggests that time doesn't exist at all, at least not in any fundamental sense. This leads to what physicists call the problem of time in quantum gravity. According to the equation, the universe should be frozen, static, unchanging. Yet here we are, distinctly aware of time's passage and surrounded by constant change. The paradox gets even stranger when we consider consciousness. If the everything formula is correct, it should describe not just physical systems, but also our experience of them. This means your current awareness, your memories, and even your sense of time passing should all emerge from this timeless mathematical structure. It's rather like discovering that the script of your life was written in a language that doesn't have any verbs. This apparent contradiction has led to various interpretations. Some physicists suggest that time might be an emergent phenomenon, like how temperature emerges from the collective behavior of particles that individually have no temperature. Others propose that consciousness itself might play a crucial role in resolving the paradox, though this ventures into philosophical territory that makes many scientists distinctly uncomfortable. The implications extend far beyond academic curiosity. If the Wheeler-DeWitt equation truly describes everything, it should also account for every decision you've ever made or will make. Your choice to read these words, your next thought, even your emotional response to this idea, all of it should be encoded in this formula. It's determinism taken to its logical extreme, raising profound questions about free will and the nature of choice. Yet the equation's very completeness might be its undoing. Kurt Gödel's incompleteness theorems suggest that any system complex enough to describe itself must contain statements that cannot be proven within that system. Applied to the everything formula, this might mean that a truly complete theory of everything is mathematically impossible. We might be seeking something that cannot exist, like trying to draw a map that includes itself. The story of the Wheeler-DeWitt equation reflects a peculiar tendency in theoretical physics. The more we attempt to understand everything, the more we bump up against the limits of understanding itself. It's as if the universe has built-in safeguards against being fully comprehended, like a cosmic version of the uncertainty principle applied to knowledge itself. What's particularly delightful about this whole situation is that we've created an equation so comprehensive that it predicts its own inability to be solved. It's rather like writing a computer program so complex that running it would require more computing power than could possibly exist in the universe. The everything formula might be correct precisely because it's impossible to fully implement. As we return to those whiteboards filled with mathematical symbols, there's something oddly comforting about the whole situation. Perhaps the universe isn't meant to be reduced to a single formula, no matter how elegant. Sometimes the most profound understanding comes not from finding the final answer, but from fully appreciating why that answer might forever remain just beyond our reach. Emergence theory. You're standing in your kitchen, staring at an ant carrying a breadcrumb across your counter. As you watch, another ant appears, then another, forming a precise line that winds efficiently around your coffee maker. Within minutes, hundreds of ants are working in perfect coordination. Though no ant is in charge, no ant understands the bigger picture, and no ant could possibly comprehend the elegant mathematical patterns they're creating. You've just stumbled upon one of the most profound and perplexing phenomena in science: emergence. The concept of emergence describes how complex systems and patterns arise from relatively simple interactions. It's the bridge between simplicity and complexity, between chaos and order, and it challenges our most basic assumptions about cause and effect. The term first appeared in scientific literature during the late 19th century, most notably in George Henry Lewis's 1875 work, Problems of Life and Mind, where he distinguished between resultance and emergence. But the idea itself has far deeper roots, reaching back to Aristotle's observation that the whole is something beside the parts. What makes emergence particularly fascinating is its ubiquity in nature. Consider a snowflake. No one tells water molecules how to arrange themselves into those intricate hexagonal patterns. There's no central planning committee, no blueprint, no master designer. The stunning complexity emerges from simple rules of molecular interaction combined with environmental conditions. The same principle applies to everything from the formation of galaxies to the patterns on seashells, from the behavior of bird flocks to the development of consciousness itself. But here's where things get properly strange. Emergence exists in distinct levels, each with its own rules and properties that can't be predicted from the level below. Take temperature, for instance. At the molecular level, there's no such thing as temperature. There's only the average kinetic energy of particles bouncing about. Temperature emerges as a property only when you have enough particles interacting. You can't understand temperature by studying a single molecule, just as you can't understand traffic patterns by studying a single car, or consciousness by studying a single neuron. This leads us to one of the most contentious aspects of emergence theory: downward causation. The idea that higher-level emergent properties can actually influence and constrain the behavior of their lower-level components seems to violate our usual understanding of causation. It's as if the traffic jam you're stuck in is controlling your car, rather than the other way around. Yet this is precisely what we observe in countless systems. The human brain serves as perhaps the most compelling example of emergence in action. The roughly 86 billion neurons in your brain, each operating on relatively simple electrochemical principles, somehow give rise to consciousness, self-awareness, and the ability to contemplate emergence theory itself. No single neuron is conscious, just as no single ant understands colony behavior, yet consciousness emerges from their collective interaction. Modern complexity theory has given us mathematical tools to better understand emergence, particularly through the study of cellular automata and agent-based models. Stephen Wolfram's work with simple computational rules producing complex patterns has shown how emergence can arise from mathematical necessity rather than chance. Stuart Kauffman's research into self-organizing systems suggests that emergence might be not just common, but inevitable under certain conditions. The implications of emergence theory extend far beyond science. In economics, Adam Smith's invisible hand describes how market economies emerge from countless individual transactions. In sociology, cultural norms and institutions emerge from individual behaviors and interactions. Even language itself is an emergent phenomenon. No one decided the rules of grammar. They emerged from patterns of human communication. Yet perhaps the most profound implication of emergence theory is what it suggests about the nature of reality itself. If complex systems can arise from simple rules, if order can emerge from chaos, if consciousness can emerge from unconscious components, then what other levels of emergence might exist beyond our current understanding? Could the physical laws we observe be emergent properties of some deeper reality? Back in your kitchen, the ant trail has completed its mission. The breadcrumb has been efficiently transported back to their colony, broken down into smaller pieces by a system of cooperation that no individual ant could have conceived. As you watch the last few stragglers return home, you might reflect that you're not just observing a simple natural phenomenon. You're watching the principles that govern the entire universe playing out on your kitchen counter. From the smallest quantum fluctuations to the largest cosmic structures, from the simplest chemical reactions to the emergence of life itself, everything we observe might just be different levels of a grand emergent symphony. Entropic gravity. You're sitting in your living room when suddenly every object starts floating upward to the ceiling. Your coffee mug, your phone, that half-eaten sandwich, all gracefully ascending as if gravity decided to take a holiday. But just before panic sets in, you notice something peculiar. The floating items aren't arranged randomly. They're organizing themselves into increasingly ordered patterns, like some cosmic game of Tetris. And that's when you realize you've stumbled upon one of physics' most mind-bending proposals. What if gravity isn't a force at all, but rather the inevitable consequence of nature's relentless pursuit of disorder? This counterintuitive idea, known as entropic gravity, emerged in 2010 when Dutch physicist Erik Verlinde published his groundbreaking paper on the origin of gravity and the laws of Newton. In it, he proposed something rather extraordinary. Gravity might not be a fundamental force of nature, but rather an emergent phenomenon arising from the underlying principles of thermodynamics and information theory. Think of it like the way temperature emerges from the collective behavior of countless particles. It's real, but it's not fundamental. The core of Verlinde's theory builds upon the holographic principle, first proposed by Gerard 't Hooft in 1993, and later refined by Leonard Susskind. They suggested that the information contained within any region of space can be described by information encoded on its boundary, rather like how a 3D image can be stored on a 2D holographic film. Verlinde took this concept further, proposing that gravity emerges from the way information about matter is encoded on these theoretical holographic screens. But here's where things get properly strange. According to entropic gravity, when two objects appear to attract each other through gravitational force, they're actually being pushed together by the universe's inexorable drive toward maximum entropy. It's rather like being at a packed music festival. You don't move toward the exit because of some mysterious exit force, but because the collective movement of the crowd naturally pushes you in that direction. The mathematics behind this idea actually reproduces Newton's laws of gravity perfectly, which is either a remarkable coincidence or a hint that we're onto something profound. This concept has fascinating implications for our understanding of dark matter. Traditional physics has struggled to explain why galaxies don't fly apart, leading to the hypothesis of invisible dark matter providing extra gravitational pull. But Verlinde's theory suggests we might not need dark matter at all. The apparent extra gravity could be an emergent effect of entropy on cosmic scales. His calculations have successfully predicted galaxy rotation curves without invoking dark matter, though the scientific community remains skeptical. The philosophical implications are equally staggering. If gravity is entropic, then one of the most fundamental aspects of our everyday experience, the simple fact that things fall down, is actually a manifestation of nature's tendency toward disorder. It's rather like discovering that your stern, rule-following physics teacher was secretly a chaos-loving anarchist all along. The universe, it seems, maintains order precisely by pursuing disorder. This connects intriguingly with black hole thermodynamics, an area pioneered by Jacob Bekenstein and Stephen Hawking in the 1970s. They showed that black holes possess entropy proportional to their surface area, not their volume, exactly what you'd expect if gravity were an entropic phenomenon. The fact that these seemingly separate ideas dovetail so neatly suggests we might be glimpsing something fundamental about the nature of space, time, and information itself. And so, we return to your living room, where objects have thankfully settled back into their normal positions. But perhaps they were never truly being pulled down by a fundamental force. Perhaps they were simply following the universe's inexorable march toward maximum entropy, like students rushing to the cafeteria at lunchtime. The apparent simplicity of gravity might be hiding a deeper truth, that the force keeping your feet on the ground is nothing more than the cosmos's desire to make a mess of things. Imaginary time. You're standing on a street corner checking your watch when suddenly time itself rotates 90 degrees. Not metaphorically, the actual dimension of time has just turned sideways, and you find yourself in a realm where what we normally call time behaves like a spatial dimension. The cars around you have become strange four-dimensional shapes stretching through both space and this peculiar sideways time. Their trajectories frozen, yet somehow still dynamic in a way your brain struggles to process. This isn't science fiction. It's precisely what theoretical physicists deal with when working with imaginary time, a mathematical transformation that turns the time dimension into something remarkably similar to space. Stephen Hawking and James Hartle first introduced this concept in 1983 as part of their no-boundary proposal for the quantum state of the universe. The mathematics involves multiplying time by the square root of -1, that notorious imaginary number that opens up entirely new realms of mathematical possibility. But what does it actually mean for time to become imaginary? In our normal experience, time and space behave quite differently. You can move freely through space in any direction, but time relentlessly marches forward. You can't decide to take a quick stroll into next Thursday or pop back to last week for tea. However, in imaginary time, these distinctions blur. Time becomes essentially another spatial dimension, allowing mathematical descriptions that would be impossible in our usual framework. This transformation isn't just a mathematical trick, it has profound implications for our understanding of the universe. When physicists apply imaginary time to quantum mechanics and gravity, something remarkable happens. The chaotic quantum fluctuations that normally characterize the beginning of the universe smooth out. The singularity that marks the Big Bang in regular time transforms into something more akin to the North Pole of time, a point that's special but not mathematically problematic, just as the North Pole is simply the northernmost point on Earth's surface. The implications extend beyond cosmology. In quantum mechanics, imaginary time helps explain how particles can appear to tunnel through barriers they shouldn't be able to cross. Picture a ball rolling up a hill. Normally, it would roll back down if it doesn't have enough energy to reach the top. But in quantum mechanics, particles sometimes appear on the other side, as if they'd tunneled straight through. Imaginary time helps explain this by showing how the particle's path can be understood as a rotation through this additional dimension. The concept also connects surprisingly to thermodynamics. When physicists calculate certain properties of materials at different temperatures, they often use imaginary time calculations. The mathematics reveals that temperature and imaginary time are intimately related. Rotating through imaginary time is mathematically equivalent to changing temperature. This connection helps explain phenomena from superconductivity to the behavior of quantum computers. But perhaps the most profound aspect of imaginary time is what it suggests about the nature of time itself. Our perception of time as fundamentally different from space might be more limited than we thought. Just as early humans couldn't conceive of negative numbers or the square root of -1, our inability to directly experience imaginary time might be a limitation of our consciousness rather than a fundamental truth about reality. Some theoretical physicists, including Hawking, have suggested that imaginary time might be more real than the time we experience. In his words, the difference between real and imaginary time might be like the difference between real and imaginary numbers, a distinction that exists in our mathematics but not necessarily in fundamental reality. Back on that street corner, as you watch the frozen yet dynamic shapes of cars stretching through this rotated dimension, you might wonder about the boundaries between what's real and what's imaginary. The mathematics of imaginary time works. It makes accurate predictions and solves real problems in physics, yet we can't experience it directly, just as we can't directly experience the fourth spatial dimension or the square root of -1. Perhaps the most remarkable aspect isn't that time could behave this way, but that human minds can conceive of and work with these concepts at all. Through mathematics, we've found a way to peek beyond the limitations of our evolved perceptions into a deeper reality. One where time itself might be just one way of slicing through a more fundamental structure of the universe. As the dimension of time rotates back to normal and you check your watch again, you might reflect that even our most basic assumptions about reality, like the distinction between time and space, could be more fluid than we imagined. In the end, imaginary time reminds us that mathematics isn't just a tool for describing the universe. It's a window into aspects of reality that lie just beyond the edge of our everyday experience. Empty space energy. You're floating in the darkest void imaginable, billions of light years from the nearest galaxy, in what should be the emptiest region of space. Yet as you drift here in the absolute darkness, your skin begins to tingle with an impossible energy, because this apparent nothingness around you is actually seething with activity at the quantum level, containing more raw energy in a cubic centimeter than all the visible matter in the known universe. This bizarre reality emerged from one of physics' most profound discoveries, that empty space isn't actually empty at all. In the 1920s, Werner Heisenberg's uncertainty principle revealed that at the quantum scale, space itself is filled with virtual particles continuously popping in and out of existence. These particle pairs appear spontaneously, exist for the briefest fraction of a second, and then annihilate each other in a never-ending quantum dance. The mathematics behind this phenomenon first appeared in Paul Dirac's groundbreaking 1928 paper on quantum electrodynamics, but it wasn't until Dutch physicist Hendrik Casimir proposed his famous experiment in 1948 that we had a way to detect this virtual particle circus. Casimir suggested placing two metal plates extremely close together in a vacuum. His calculations showed that the restricted space between the plates would allow fewer virtual particles to appear there than in the surrounding space, creating a tiny but measurable attractive force between the plates. This Casimir effect was finally measured in 1997 by Steve Lamoureux at Los Alamos National Laboratory, confirming that empty space contains this remarkable underlying energy. But here's where things get properly strange. When physicists calculated how much energy should be present in the quantum vacuum, they arrived at a number so absurdly large, it threatens to break our understanding of the universe. The theoretical energy density of empty space works out to be 10 to the power of 93 grams per cubic centimeter. To put that in perspective, if we took a volume of vacuum the size of a sugar cube, it should contain enough energy to boil all Earth's oceans, not just once, but billions of times over. The entire visible universe only has a mass energy of about 10 to the 51st grams. The vacuum energy in your coffee cup should be enough to create a new universe. This presents us with what physicists call the vacuum catastrophe. possibly the largest disagreement between theory and observation in all of science, because clearly, this enormous energy isn't expressing itself in ways we can detect. If it did, space itself would be torn apart. The measured cosmological constant, which represents the energy density of space, is somehow 120 orders of magnitude smaller than what quantum mechanics predicts. The implications ripple far beyond this mathematical mismatch. This vacuum energy might be responsible for the mysterious dark energy causing our universe's acceleration. Some theories suggest it could have powered cosmic inflation in the earliest moments after the Big Bang. It might even allow for the spontaneous creation of universes from nothing, a concept that would have made both Einstein and Newton spill their tea. But perhaps the most mind-bending aspect is what this tells us about the nature of nothing itself. We tend to think of empty space as a blank canvas on which the universe paints its contents. Instead, it appears to be more like a roiling ocean of quantum foam, with particles borrowing energy from the future to briefly exist before paying it back through their annihilation. This connects to an even deeper principle in quantum mechanics, that there's no such thing as truly empty space. The quantum fields that permeate the universe must always have at least their zero-point energy, like a quantum guitar string that can never be completely still. Even at absolute zero temperature, these fields maintain a constant, irreducible amount of activity. Modern physics suggests we might need to fundamentally revise our concept of nothingness. The vacuum isn't a void. It's a complex, dynamic system that might hold the key to understanding the universe's biggest mysteries. From the expansion of space to the possibility of spontaneous universe creation, this quantum frothing of the vacuum could be the foundation of everything we observe. As you float here in the intergalactic void, that tingling sensation takes on new meaning. You're not surrounded by emptiness at all, but by an ocean of potential reality itself, where the very fabric of space-time is alive with quantum possibilities. Perhaps what we call nothing is actually the most interesting something of all. Quantum teleportation. You're standing in a laboratory in Vienna, holding a sealed envelope containing launch codes for a nuclear missile. A team of scientists has just activated their quantum teleportation device, and in an instant, the exact quantum state of every particle making up that envelope and its contents has vanished, only to reappear perfectly intact in a lab in Beijing. The envelope in your hands has been reduced to meaningless particles, while its perfect twin now exists 7,400 kilometers away. But here's the truly mind-bending part. According to the laws of quantum mechanics, it's fundamentally impossible to know what was actually in that envelope, even though it was just perfectly teleported across the planet. This isn't science fiction. It's a real phenomenon called quantum teleportation, first demonstrated in 1997 by Anton Zeilinger's team at the University of Innsbruck. The process relies on one of quantum mechanics' most bizarre features: quantum entanglement, what Einstein famously called spooky action at a distance. When two particles become entangled, their quantum states become inextricably linked, regardless of how far apart they are. The breakthrough paper, published in Nature by Baumeister and colleagues, showed how entanglement could be used to transmit quantum information. The key insight was that while you can't directly copy a quantum state, due to the no-cloning theorem, you can use entanglement to destroy the original state and reconstruct it perfectly somewhere else. Here's where things get properly strange. The process requires three particles, the one you want to teleport, let's call it A, and an entangled pair, B and C. Particle B is with you and the original, while C is at the destination. When you perform a specific measurement on A and B together, something remarkable happens. The act of measurement forces particle C, potentially light years away, to instantly adopt a state related to A's original state. But there's a catch. You need to send some additional classical information before the teleportation is complete. The mathematics behind this is beautifully elegant, even if it seems to defy common sense. The quantum state being teleported can be thought of as a point on a sphere, the Bloch sphere, to be precise. The entangled particles provide a sort of quantum coordinate system that allows this point to be precisely reconstructed at the destination. But the truly bizarre aspect is that the quantum information seems to travel instantaneously through the entanglement channel, while we still need to send classical information at the speed of light to complete the process. This leads us to a fascinating philosophical question. What exactly is being teleported? It's not matter. The particles themselves stay put. It's not energy. No energy is transmitted faster than light. It's pure information, but of a fundamentally quantum nature. Unlike classical information, quantum information exists in a superposition of states until measured, following rules that seem to mock our classical intuitions. The implications extend far beyond just moving quantum states around. Quantum teleportation is a cornerstone of quantum computing and quantum cryptography. In 2017, Chinese scientists used the Möbius satellite to demonstrate quantum teleportation over 1,400 kilometers, bringing us closer to a quantum internet, a network where quantum information can be transmitted with perfect security guaranteed by the laws of physics themselves. But perhaps the most profound aspect is what quantum teleportation tells us about information itself. In classical physics, information is almost an afterthought, a way of describing physical systems. But in quantum mechanics, information appears to be fundamental. The fact that quantum states can be teleported suggests that information might be more basic to the universe than matter or energy. This connects to a broader theory gaining traction in physics, that information might be the fundamental stuff of reality. John Wheeler captured this idea in his famous phrase, "it from bit," suggesting that physical things, it, might emerge from information, bit. Quantum teleportation provides a tantalizing glimpse of how deep this rabbit hole might go. The next time you send a text message, remember that while your classical bits are trudging along at the speed of light, quantum teleportation is already routinely achieving what Star Trek only dreamed of, though admittedly, only for individual quantum states rather than Captain Kirk. The envelope with those launch codes might have to wait a while longer, but the quantum future is already here, and it's stranger than we could have imagined. Time crystals. You're frozen in perfect stillness, yet somehow you're moving. Every atom in your body repeats the exact same pattern over and over, like a dance sequence playing on an infinite loop. You haven't broken any laws of physics, quite the opposite. You've become part of a time crystal, one of the strangest forms of matter ever created, and you're experiencing firsthand what it means to have perpetual motion without breaking the rules of thermodynamics. The story of time crystals begins with a seemingly absurd question posed by Nobel laureate Frank Wilczek in 2012. If regular crystals show spatial symmetry by repeating patterns in space, could there be crystals that repeat patterns in time? The immediate response from most physicists was absolutely not. Such a thing would violate fundamental laws of physics, particularly the second law of thermodynamics. But Wilczek's question sparked a theoretical framework that would eventually lead to one of the most bizarre discoveries in modern physics. To understand time crystals, we first need to grasp what makes regular crystals special. In a normal crystal, like a diamond or table salt, atoms arrange themselves in patterns that repeat in space. If you slide the crystal over by exactly the right distance, it looks identical to its original position. This spatial symmetry is what gives crystals their regular structure. Time crystals do something similar, but instead of repeating patterns in space, they repeat patterns in time, without using any external energy. Now this might sound like perpetual motion, which we know is impossible, but time crystals manage to sidestep this prohibition through the strange rules of quantum mechanics. In 2016, researchers at the University of Maryland created the first time crystal using a chain of ytterbium ions. They hit these ions with laser pulses that flipped their quantum states. Under normal circumstances, these flips should eventually settle into a random pattern due to entropy. But something extraordinary happened. The ions started flipping at twice the rate of the driving pulses, creating a pattern that repeated in time indefinitely. The implications of this discovery stretch far beyond mere scientific curiosity. Time crystals represent a completely new phase of matter, one that exists not in thermal equilibrium like every other phase we know. They're the first example of a non-equilibrium phase that remains stable, a possibility that physicists had long thought impossible. It's as if you had a pot of water that continued to ripple in a perfect pattern forever without any energy input, but the rabbit hole goes deeper. Time crystals also challenge our understanding of the arrow of time itself. In our everyday experience, time flows in one direction. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. This one-way street is governed by the second law of thermodynamics, which states that entropy, disorder, always increases. Time crystals seem to thumb their nose at this universal tendency toward disorder, maintaining their rhythmic dance indefinitely. The applications of time crystals could be equally mind-bending. Quantum computers, for instance, face a major challenge in maintaining quantum states long enough to perform calculations. Time crystals' ability to maintain stable patterns indefinitely could provide a solution. Their unique properties might also lead to new forms of precision timekeeping, or help us understand how order can emerge and persist in far from equilibrium systems. Perhaps most intriguingly, time crystals force us to reconsider what we mean by equilibrium and stability. We typically think of stable systems as those that don't change, a ball resting at the bottom of a bowl, a planet in a circular orbit. But time crystals achieve stability through constant motion, like a cyclist who can only maintain balance while moving forward. The philosophical implications spiral outward from here. If matter can find stability through perpetual change, what does this tell us about the nature of permanence itself? Are there other systems, biological, social, or cosmic, that maintain their integrity not through stillness, but through carefully choreographed motion? As you continue your endless dance in the time crystal, you might reflect on how this quantum oddity embodies a profound paradox. Sometimes the only way to stay the same is to keep changing. In a universe that seems destined to wind down into uniform disorder, time crystals remind us that nature still has secrets up its sleeve, secrets that challenge our most fundamental assumptions about the fabric of reality itself. The nothing force. You're standing on the edge of the universe, gazing into an infinite void of perfect emptiness, when suddenly you feel it, a mysterious push coming from absolutely nothing at all. This isn't science fiction. It's one of the most peculiar phenomena in modern physics, and it's happening right now throughout every cubic centimeter of space, including the room where you're sitting. The nothing force, more formally known as the Casimir Effect, stands as one of quantum mechanics' most startling predictions. Empty space itself can generate measurable physical force. In 1948, Dutch physicist Hendrik Casimir made a rather odd prediction while studying the properties of colloidal solutions at Phillips Research Labs. He proposed that if you place two parallel metal plates extremely close together in a vacuum, they should experience a tiny attractive force. The revolutionary aspect wasn't the force itself, it was its source. According to Casimir's calculations, this force emerged from the quantum fluctuations of absolutely empty space. The quantum vacuum, it turns out, isn't actually empty at all. At the smallest scales, space resembles a roiling sea of virtual particles popping in and out of existence faster than we can measure. These quantum fluctuations create what physicists call zero-point energy, the lowest possible energy state of any quantum system. Between those parallel plates Casimir described, some of these fluctuations get restricted. Outside the plates, the full spectrum of quantum fluctuations can occur, but between them, only certain wavelengths can exist, like a guitar string that can only vibrate at specific frequencies. This restriction creates an imbalance. The fuller spectrum of quantum fluctuations outside the plates ends up pushing them together, a force born from nothingness itself. The effect is minuscule, becoming noticeable only when the plates are placed nanometers apart, but it's very real. In 1997, Steve Lamoureux at Los Alamos National Laboratory first measured the Casimir force experimentally, confirming Casimir's predictions with remarkable accuracy. The implications reach far beyond laboratory curiosities. The Casimir effect demonstrates that empty space has structure and can influence the physical world. It's as if the vacuum itself harbors hidden energy waiting to manifest under the right conditions. This connects to one of modern physics' most puzzling mysteries: dark energy, the unknown force causing our universe's acceleration-expansion. Some physicists have suggested that dark energy might be related to zero-point energy of the quantum vacuum, essentially a cosmic-scale version of the Casimir effect. However, the math presents a rather embarrassing problem. When theorists calculate how much zero-point energy should exist in the vacuum of space, they get a number that's wrong by 120 orders of magnitude, possibly the largest disagreement between theory and observation in the history of science. The nothing force also plays havoc with our intuitions about cause and effect. How can nothing cause something? The answer lies in quantum mechanics' probabilistic nature. The uncertainty principle ensures that even in absolute vacuum, energy and time can't both be precisely zero. These unavoidable fluctuations in the quantum vacuum are as fundamental to reality as space and time themselves. This leads us to a profound question about the nature of emptiness. If true nothingness can't exist, if empty space itself contains structure, energy, and force, then what does it mean for something to be nothing at all? The philosophical implications echo ancient debates. The Greek philosopher Parmenides argued that true nothingness was impossible because even thinking about nothing requires it to be something. The Casimir effect seems to provide experimental support for this ancient intuition. The nothing force also challenges our understanding of virtual particles. These quantum fluctuations aren't virtual in the sense of being unreal. They have measurable effects on the physical world. They're virtual only in the sense that they exist too briefly to be directly observed. It's as if reality itself contains a substrate of possibility, occasionally crystallizing into measurable effects under the right conditions. Modern applications of the Casimir effect range from practical to speculative. On the practical side, it becomes relevant in nanotechnology, where components can be small enough for the force to affect their operation. More speculatively, some researchers have proposed using the effect to stabilize theoretical wormholes in spacetime or to extract useful energy from the quantum vacuum. As you sit here contemplating these quantum fluctuations in the seemingly empty space around you, consider that you're surrounded by an ocean of virtual particles, their brief existences contributing to a force that reminds us how little we truly understand about nothingness. The void, it seems, is anything but empty, and in that paradox lies one of nature's most profound mysteries. Quantum foam. You're shrinking. Not in the conventional sense of getting smaller while maintaining your basic structure, but in a far more profound way. You're actually becoming tiny enough to witness the fabric of space-time itself. At about 10 to 35 meters, far smaller than any subatomic particle, you begin to see something utterly bizarre. The supposedly smooth continuum of space and time breaks down into a violent, chaotic froth of virtual particles popping in and out of existence, microscopic black holes forming and evaporating in fractions of a second, and the fundamental forces of nature becoming indistinguishable from one another. This roiling, dynamic structure is quantum foam, first proposed by John Wheeler in 1955. Wheeler was wrestling with the fundamental conflict between quantum mechanics and general relativity, the physics of the very small versus the physics of the very large. At normal scales, space-time appears smooth and continuous, much like how a calm ocean looks flat from an airplane. But just as that ocean reveals its waves and ripples as you get closer, Wheeler suggested that space-time itself becomes increasingly turbulent at microscopic scales. The mathematics behind quantum foam emerge from Heisenberg's uncertainty principle. At extremely small scales, the uncertainty in energy and time becomes so significant that particles can spontaneously appear and disappear without violating conservation laws. These virtual particles create minute distortions in space-time, similar to how bubbles create disturbances in boiling water. But unlike boiling water, quantum foam exists in 4 dimensions, with time itself becoming part of this chaotic dance. The implications are staggering. Every cubic centimeter of seemingly empty space contains an amount of energy that, if converted to matter, would create a mass greater than all the visible stars in the universe. This vacuum energy, or zero-point energy, is a direct consequence of quantum foam's existence. The only reason we don't experience this enormous energy in everyday life is that it operates at scales so small that its effects average out at our level of existence. Werner Heisenberg himself once remarked that the structure of space at these minute scales would make Dante's Inferno seem like a child's playground. He wasn't exaggerating. At the Planck scale, where quantum foam becomes dominant, our conventional understanding of physics breaks down entirely. The distinction between matter and energy becomes meaningless. The arrow of time loses its direction. Even the number of dimensions becomes uncertain, with some theories suggesting that space itself might have as many as 11 dimensions at this scale. The existence of quantum foam might explain one of the most puzzling aspects of modern physics, the cosmological constant problem. When theoretical physicists calculate how much vacuum energy space should contain based on quantum mechanics, they get a number that's 120 orders of magnitude larger than what we observe. This discrepancy represents the largest gap between theoretical predictions and experimental observations in all of science. Quantum foam might hold the key to resolving this contradiction, though the exact mechanism remains elusive. But the implications of quantum foam extend beyond pure physics into philosophy. If space itself isn't fundamentally continuous, but discrete and granular at the smallest scales, what does this mean for our understanding of reality? The ancient Greek philosopher Zeno posed paradoxes about infinite divisibility that seem eerily prescient in light of quantum foam. Perhaps space isn't infinitely divisible after all. There might be a fundamental unit of length below which measurement becomes meaningless. Recent proposals suggest that quantum foam might be detectable through its effects on light traveling from distant galaxies. As photons traverse billions of light years, tiny interactions with quantum foam could cause subtle changes in their properties. Several experiments are currently underway using gamma-ray telescopes to look for these effects, though definitive evidence remains elusive. The presence of quantum foam also raises intriguing questions about the nature of information and the limits of computation. Seth Lloyd of MIT has calculated that the ultimate laptop, one that uses the maximum amount of computing power possible in a given volume of space, would be limited by the granularity of quantum foam. The smallest possible unit of information storage would correspond to a single Planck volume of space. As we return to our normal scale, leaving behind the violent quantum froth, we're left with a profound realization. The smooth, continuous space we experience is an illusion. Reality, at its most fundamental level, is discrete, probabilistic, and far stranger than our everyday experience suggests. The calm surface of space-time masks a seething ocean of quantum possibilities, forever hidden from direct observation, but fundamental to the very structure of our universe. Quantum memory. You're sitting in your favorite chair, trying to remember where you left your keys. As you retrace your mental steps, a curious thought strikes you. Those memories you're sifting through don't actually exist anywhere specific in your brain. They're distributed across billions of neurons in a complex quantum dance of possibility. In fact, your keys themselves exist in a similar state of quantum uncertainty until you actually observe them. Now imagine if we could harness this quantum nature of reality, not just for losing keys, but for storing and processing information in ways that would make your misplaced key problem trivially solvable. Welcome to the strange world of quantum memory. The concept of quantum memory emerged from the intersection of quantum mechanics and information theory in the late 1990s. While classical computers store information in bits that are either 0 or 1, Quantum memory works with quantum bits or qubits that can exist in multiple states simultaneously through a phenomenon called superposition. This idea was first formally described in a groundbreaking 1995 paper by Benjamin Schumacher, who showed how quantum states could be compressed and stored, essentially creating the theoretical foundation for quantum memory. The real magic of quantum memory lies in its ability to maintain quantum coherence, the delicate state where qubits remain in superposition. Think of it like trying to balance a pencil on its tip. Classical information is like letting the pencil fall one way or the other, while quantum memory keeps it perfectly balanced, maintaining all possibilities at once. This property allows quantum memory to store exponentially more information than classical memory. A system of just 300 qubits could store more states than there are atoms in the observable universe. But maintaining this quantum coherence is fiendishly difficult. The slightest interaction with the environment can cause decoherence, essentially collapsing the quantum state. It's rather like trying to keep that pencil balanced while the Earth is being bombarded by cosmic rays, experiencing minor earthquakes, and being subjected to the gravitational pull of every passing asteroid. This challenge led to the development of quantum error correction codes, first proposed by Peter Shor in 1995, which protect quantum information by encoding it across multiple physical qubits. The implications of quantum memory extend far beyond simply storing more data. In 2001, researchers at Harvard and Oxford demonstrated that quantum memory could be used to create quantum repeaters, devices that could extend the range of quantum networks by storing and retransmitting quantum states. This breakthrough opened up possibilities for quantum internet, where information could be transmitted with perfect security, guaranteed by the laws of physics themselves. Perhaps even more fascinating is how quantum memory relates to our understanding of time itself. In 2013, a team at the Australian National University showed that quantum memory could be used to simulate time travel scenarios, specifically studying how quantum particles would behave if they could interact with their past selves. While this doesn't mean we'll be building time machines anytime soon, it reveals profound connections between information, quantum mechanics, and the nature of time. The philosophical implications are equally mind-bending. If quantum memory can exist in multiple states simultaneously until observed, what does this tell us about the nature of reality itself? The famous quantum physicist John Wheeler proposed that information might be the fundamental building block of the universe, more basic than matter or energy. In this view, quantum memory isn't just a technology, it's a window into the deep structure of reality. As we sit here contemplating these possibilities, perhaps those lost keys exist in a quantum superposition of all possible locations until we collapse their wave function by finding them. Though that might not help us find them any faster, it certainly makes the search more philosophically interesting. 0-point motion. You're completely frozen in place, having achieved absolute zero temperature, the coldest possible state in the universe. Every particle in your body has stopped moving entirely. Except that's not what's happening at all. Even in this theoretical state of perfect cold, your atoms are still dancing about rather energetically, defying everything we thought we knew about motion and temperature. Welcome to one of quantum mechanics' most peculiar phenomena, 0-point motion. Back in 1911, Max Planck and his colleagues were wrestling with a profound puzzle. Classical physics insisted that at absolute zero, all molecular motion should cease entirely. But their calculations kept showing something impossible. Atoms that wouldn't stay still, no matter how cold they got. This quantum jitteriness wasn't just some mathematical curiosity. It turned out to be fundamental to how our universe works. The mathematics behind 0-point motion emerged from Heisenberg's uncertainty principle, published in 1927. The principle states that we can't simultaneously know both the position and momentum of a particle with perfect precision. This isn't just about measurement limitations. It's a fundamental feature of reality. The more precisely we pin down where something is, the more uncertain its momentum becomes, and vice versa. Think of an atom as if it were trapped in an invisible box. Classical physics would say that at absolute zero, the atom should sit perfectly still at the bottom of the box. But quantum mechanics reveals something rather different. By trying to confine the atom to a precise position, we've made its momentum highly uncertain. This uncertainty manifests as motion, not regular, predictable motion, but a constant quantum wiggle that never stops. The implications are staggering. Even at absolute zero negative 273.15 degrees Celsius or 0 Kelvin, when we've removed every bit of thermal energy possible, particles retain what we call zero-point energy. It's like trying to empty a cup that magically refills itself with a tiny bit of water every time you think you've gotten the last drop out. This isn't just theoretical musing. Zero-point motion has real, measurable effects. In 1948, Hendrik Casimir predicted that this quantum jittering would create a tiny attractive force between two parallel metal plates in a vacuum. The force was experimentally measured in 1997, proving that empty space isn't really empty at all. It's buzzing with quantum fluctuations. But the rabbit hole goes deeper. Zero-point motion plays a crucial role in keeping matter stable. Take helium, for instance. At atmospheric pressure, liquid helium won't freeze, even at absolute zero. The zero-point motion of its atoms provides enough energy to prevent the formation of a crystal structure. It's rather like having a group of children who are so naturally energetic that they can't sit still even when told to freeze completely. The phenomenon also helps explain why certain chemical reactions continue even at extremely low temperatures. When scientists cool molecular hydrogen to near absolute zero, they observe that quantum tunneling, a process directly related to zero-point motion, allows reactions to proceed that classical physics says should be impossible. These quantum effects scale up in surprising ways. The zero-point motion of electrons in metals contributes to their electrical conductivity. In biological systems, it may even play a role in enzyme catalysis and quantum tunneling during photosynthesis. We're discovering that this fundamental quantum wiggle might be essential to life itself. The philosophical implications are equally profound. The fact that nothing can ever be truly motionless challenges our basic intuitions about rest and motion. It suggests a universe that's intrinsically dynamic at its smallest scales, where perfect stillness is not merely difficult to achieve, it's fundamentally impossible. Some theorists have even suggested that zero-point motion might be connected to dark energy, the mysterious force causing our universe's expansion to accelerate. The energy of quantum fluctuations in empty space could, in principle, contribute to this cosmic push, though the calculations don't quite add up yet. As we return to our thought experiment of being frozen at absolute zero, we can appreciate the beautiful absurdity of it all. Every atom in your body would still be dancing to quantum mechanics' strange tune, maintaining a perpetual jig that no amount of cooling can stop. It's rather like discovering that the universe has an irrepressible sense of rhythm. Even in its coldest, quietest moments, it simply can't help but dance. Biocentrism Theory. You're lying in bed at 3 a.m. staring at your ceiling, when suddenly you realize the ceiling isn't actually there. In fact, you're not even there. The entire universe, with its vast expanse of galaxies, stars, and that suspicious stain above your bed that you've been meaning to clean, might only exist because you're conscious of it. Your brain is creating reality itself, and if you fell asleep right now, would anything continue to exist at all? Before you dismiss this as a classic case of late-night existential crisis, you should know that a rather respected scientist named Robert Lanza has spent considerable time arguing that this might be exactly how the universe actually works. This peculiar perspective on reality is known as Biocentrism Theory, formally introduced by Lanza in his 2009 book, Biocentrism: How Life and Consciousness Are the Keys to Understanding the True Nature of the Universe. The theory proposes that consciousness creates the universe, rather than the other way around. It's a radical departure from the traditional view that the universe is an independent physical entity that existed long before conscious life emerged. Instead, biocentrism suggests that space and time aren't physical things at all, but rather tools our consciousness uses to weave information together in a coherent way. The foundations of this theory didn't materialize from nowhere. They're deeply rooted in some of the most puzzling aspects of quantum mechanics, particularly the famous double-slit experiment, first conducted by Thomas Young in 1801 and later refined in countless variations. In this experiment, particles seem to behave differently when they're being observed, suggesting that consciousness somehow influences physical reality at the quantum level. The Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg in the 1920s, had already hinted at the strange role of consciousness in physical reality. But biocentrism takes this idea to its logical, if somewhat mind-bending, extreme. Lanza's theory rests on several principal claims, each more extraordinary than the last. First, it suggests that what we perceive as space and time are actually forms of animal sense perception, rather than external physical objects. Consider how your dog experiences the world primarily through smell, creating a reality vastly different from your visual one, yet both are equally valid interpretations of the same underlying reality. Biocentrism suggests that space and time work similarly. They're tools our consciousness uses to make sense of information, rather than fundamental aspects of reality. The theory goes further, proposing that the structure of the universe itself is determined by the biological apparatus with which we observe it. This isn't as outlandish as it might first sound. After all, we know that bees see ultraviolet patterns in flowers that are invisible to us, and mantis shrimp have 16 color receptors compared to our mere 3. Each species literally sees a different universe. Biocentrism suggests that these aren't just different perspectives on a fixed reality, but rather different realities themselves, each created by the consciousness observing them. This leads to one of biocentrism's most controversial implications, the suggestion that death might not be the end of consciousness, but rather a transition in how consciousness experiences reality. Since space and time are products of consciousness rather than external realities, the theory suggests that consciousness might exist independent of these constraints. It's rather like suggesting that a character in a video game doesn't cease to exist when you turn off the console. They simply stop experiencing that particular version of reality. The scientific community has responded to biocentrism with a mixture of fascination and skepticism. Critics argue that the theory makes claims that are effectively impossible to test experimentally, placing it in the awkward territory between scientific hypothesis and philosophical speculation. However, supporters point out that many of our most fundamental scientific theories, including string theory, face similar challenges of testability. Perhaps the most intriguing aspect of biocentrism is how it connects to ancient philosophical questions about the nature of reality. Buddhist philosophers have long argued that consciousness plays a fundamental role in creating our experience of reality, and the ancient Greek philosopher Berkeley proposed that physical objects only exist as ideas in minds. Biocentrism effectively gives these ancient philosophical insights a modern scientific framework, suggesting that the most cutting-edge physics might be leading us back to some very old wisdom indeed. As you lie there contemplating whether your ceiling exists when you're not looking at it, you might take comfort in knowing that you're participating in one of humanity's oldest and most profound philosophical investigations. Whether or not biocentrism ultimately proves correct, it reminds us that reality might be far stranger than our everyday experience suggests. And perhaps that suspicious stain on your ceiling isn't really there after all, at least until you look at it again in the morning. Quantum eraser. You're standing in front of 2 doors at the quantum physics department, desperately needing to use the bathroom. A helpful British physicist explains that both doors lead to the same bathroom, but due to a quantum mechanics experiment gone wrong, using either door will cause you to arrive through the other, unless, that is, someone erases the record of which door you chose, in which case you'll arrive through both doors simultaneously, while also keeping your particles to yourself. Welcome to the bizarre world of quantum erasure. where information itself shapes the fundamental nature of reality. The quantum eraser experiment, first proposed by Scully and Druhl in 1982, builds upon the famous double-slit experiment that had already been confounding physicists since Thomas Young introduced it in 1801. In the classic version, particles fired at a screen with two slits create an interference pattern suggesting each particle travels through both slits simultaneously, unless we measure which slit it goes through, in which case the interference pattern disappears. The quantum eraser took this peculiar phenomenon a step further by asking, what happens if we measure which path the particle takes, but then erase that information before looking at the results? The experimental setup involves pairs of entangled photons, with one photon going through the double slits while its partner carries the which path information. When scientists measure the partner photon in a way that preserves path information, the first photon behaves like a particle. But if they measure the partner photon in a way that erases the path information, the first photon's interference pattern reappears, even if this erasure happens after the first photon has already been detected. This seemingly retroactive effect challenges our basic understanding of causality and the nature of time itself. Dr. Marlon Scully's team at the University of California, Berkeley, demonstrated this effect using a clever arrangement of beam splitters and polarizers. Their 1991 paper, in Nature, showed that quantum mechanics allows for what Einstein once dismissively called spooky action at a distance to work backwards in time. It's as if the photon somehow knows its future measurement before it happens, or perhaps more accurately, as if time itself operates differently at the quantum level than it does in our everyday experience. The implications of the quantum eraser extend far beyond physics laboratories. Consider the nature of information itself. What we traditionally think of as abstract knowledge appears to have direct physical consequences at the quantum level. This suggests a deep connection between information and physical reality that philosophers have only begun to explore. Some theorists, like John Wheeler, propose that information might be as fundamental to the universe as matter and energy, leading to his famous it from bit hypothesis. This brings us to two fascinating philosophical questions. First, what does it mean for something to be measured in quantum mechanics? The Copenhagen interpretation suggests that measurement itself causes the quantum wave function to collapse into a definite state, but this raises thorny questions about consciousness and observation. Does an automated detector count as a measurement? Does a cat? Does a bacterium? The quantum eraser experiment suggests that measurement might be better understood as the creation of information rather than a physical interaction. Secondly, the quantum eraser challenges our understanding of causality itself. If erasing information about a particle's path can retroactively change its behavior from particle-like to wave-like, what does this tell us about the nature of cause and effect? Some physicists, like John Cramer, have proposed a transactional interpretation of quantum mechanics, where particles exchange information both forwards and backwards in time. Others suggest that our entire conception of linear time might be an emergent property rather than a fundamental aspect of reality. So the next time you're faced with a choice between two paths, remember that at the quantum level, the very existence of information about which path you took might be what forces you to take one or the other. Perhaps it's not the choice that matters, but rather what the universe remembers about it. Though I suppose in the case of our quantum bathroom, it's probably best to just hold it and find a nice classical loo instead. Hypercubes in nature. You're walking through a garden on a misty morning, admiring the delicate crystalline structure of a spider's web stretched between two rose bushes. As you lean in closer, the dewdrops catching the early light, something extraordinary happens. The web begins to shift and extend, not outward or inward, but somehow elsewhere. The strands stretch into impossible geometries, and suddenly you're seeing not just the familiar 3 dimensions of the web, but a fourth spatial dimension unfolding before your eyes. You've just stumbled upon one of nature's most bizarre secrets. Hidden hypercubes are everywhere, from the molecular structure of water to the fundamental fabric of space-time itself. The concept of a hypercube, or tesseract, was first mathematically described by Charles Howard Hinton in 1884. It's a four-dimensional analog of our familiar cube, just as a cube is a three-dimensional analog of a square. But unlike the leap from 2D to 3D, which we can easily visualize, the jump to 4D challenges our evolved perception of reality. Yet remarkably, nature seems to have no such limitations. Take water molecules, for instance. When water freezes into ice, its molecules arrange themselves into tetrahedral structures, three-dimensional pyramids with triangular faces. But the quantum mechanics governing these molecules' behavior actually operates in four spatial dimensions. The hydrogen bonds that hold water molecules together don't just connect in our visible three dimensions. They exhibit what physicists call quantum tunneling, where protons can exist in multiple positions simultaneously, creating a fourth spatial dimension of possible configurations. This isn't just theoretical abstraction. In 2016, researchers at Harvard University discovered that certain quantum systems, when cooled to near absolute zero, form structures that can only be properly described using four spatial dimensions. They observed particles arranging themselves in patterns that, while existing in our three-dimensional space, followed rules that only make sense in four dimensions. The implications extend far beyond frozen water. Living systems, too, show evidence of hyperdimensional organization. The way proteins fold into their functional shapes involves movements that, mathematically speaking, require four spatial dimensions to describe completely. It's as if nature found a way to perform origami in higher dimensions, then project the results into our more limited three-dimensional experience. Even more remarkable is how these natural hypercubes manifest in the structure of DNA. The famous double helix isn't just a three-dimensional spiral. Its electromagnetic properties create what physicists call a configuration space that exists in four spatial dimensions. When DNA replicates, it performs topological gymnastics that, while appearing to us as simple unwinding, actually involves movements through this fourth dimension. The rabbit hole goes deeper when we consider the role of hypercubes in fundamental physics. Einstein's theory of special relativity essentially reveals that time itself is a fourth dimension, geometrically identical to space dimensions. This means that every object in the universe, including you reading this right now, is actually a four-dimensional world line extending through space-time. We only perceive three-dimensional slices of reality moment by moment, like a two-dimensional being trying to understand a cube by looking at its cross-sections. But perhaps the most mind-bending aspect of natural hypercubes appears in quantum field theory. The mathematical frameworks that describe particle interactions require not just four, but potentially 10 or 11 spatial dimensions. These extra dimensions might be compactified, rolled up so tiny we can't detect them directly, but they're essential to explaining how the universe works at its most fundamental level. Coming back to that spider's web in the garden, its seemingly simple structure hints at these higher dimensional realities. The spider, through millions of years of evolution, has developed the ability to create structures that optimize four-dimensional problems of tensile strength and spatial efficiency, without any awareness of the mathematics involved. The web's geometry, when analyzed at the molecular level, displays patterns that mirror the mathematics of higher dimensional spaces. As the morning mist begins to clear and the web returns to its familiar three-dimensional appearance, we're left with a profound realization. Our perceived reality might be just a shadow of a much richer, higher dimensional universe. Like the inhabitants of Edwin Abbott's Flatland, we're surrounded by evidence of dimensions we can't directly perceive, yet they shape everything from the water we drink to the DNA in our cells. Looking at that spider's web one last time, you might notice how the dewdrops catch the light differently now, each one potentially containing reflections of geometric truths that extend far beyond our limited three-dimensional perception. Quantum biology. You're lying in bed at night, staring at the ceiling, when suddenly you realize your nose is detecting the scent of coffee from your neighbor's kitchen. A completely ordinary occurrence, except that according to classical physics, those coffee molecules should never have made it through your bedroom wall. Yet here you are, experiencing quantum tunneling through your olfactory receptors, your body casually defying classical physics while you contemplate tomorrow's breakfast. The bizarre intersection of quantum mechanics and biology has puzzled scientists since the early days of quantum theory. In 1944, Erwin Schrödinger published his groundbreaking book, What is Life?, logically suggesting that quantum mechanics might play a crucial role in biological processes. At the time, most physicists dismissed the idea. Quantum effects were thought to only exist in carefully controlled laboratory conditions at temperatures approaching absolute zero. The warm, wet, chaotic environment of living cells seemed completely incompatible with the delicate quantum states they studied. Yet nature, as it often does, had other plans. In 2007, researchers at UC Berkeley demonstrated that European robins use quantum entanglement in their navigational system. The bird's retinas contain cryptochrome proteins that create pairs of quantum-entangled electrons when struck by light. These entangled pairs are sensitive to Earth's magnetic field, giving the robins an internal quantum compass. The real shock wasn't just that quantum effects could exist in biological systems, it was that they were essential to life itself. The rabbit hole goes deeper. That coffee smell you detected. It turns out your sense of smell likely relies on quantum tunneling, where electrons pass through energy barriers they classically shouldn't be able to cross. Dr. Luca Turin's controversial quantum theory of olfaction suggests that when molecules arrive at your olfactory receptors, electrons tunnel between different energy states, with the specific quantum vibrational frequencies determining which smell you perceive. While debate continues about the exact mechanism, recent evidence increasingly supports the role of quantum effects in how we detect odors. But perhaps the most remarkable example of quantum biology happens every time you look at anything at all. Photosynthesis, the process that powers most life on Earth, achieves its extraordinary efficiency through quantum coherence. When a photon strikes a leaf, it creates an excited electron that needs to find its way to the reaction center, where its energy can be harvested. Classical physics would predict a relatively inefficient random walk. Instead, the electron exists in a quantum superposition, simultaneously exploring multiple paths like a quantum search algorithm, finding the most efficient route with remarkable speed. The implications extend far beyond simple efficiency. The fact that evolution has apparently learned to harness quantum effects challenges our understanding of both biology and quantum mechanics. These aren't just edge cases or curious accidents, they're essential features of life itself. Quantum coherence in photosynthesis, for instance, works at room temperature and maintains its quantum states far longer than our best engineered systems. Nature has somehow solved problems that continue to baffle our quantum computer engineers. This convergence of quantum mechanics and biology raises profound questions about the nature of life itself. If quantum effects are fundamental to basic biological processes like photosynthesis, navigation, and smell, what else might they influence? Some researchers speculate about quantum effects in consciousness, though that remains highly controversial. Others investigate potential quantum roles in enzyme catalysis, DNA mutation, and even the origin of life itself. The study of quantum biology also offers practical applications. Understanding how nature maintains quantum coherence in warm, wet environments could revolutionize quantum computing. The remarkable efficiency of photosynthesis is already inspiring better solar cell designs. Even the humble robin's quantum compass might help us develop more precise navigation systems. As you lie there in bed, detecting impossibly tunneled coffee molecules, consider that your body is performing quantum calculations that would put our most advanced computers to shame. You're not just a collection of classical chemical reactions, you're a quantum mechanical miracle, routinely accomplishing feats that should be impossible according to classical physics. Perhaps that's worth contemplating over tomorrow morning's quantum-tunneled coffee. Tachyonic Antitelephones. You're standing in your kitchen at exactly 6 p.m., calmly stirring a pot of pasta, when suddenly your phone rings. The caller ID shows it's you, calling from 5:59 p.m. Your past self has an urgent message: don't use so much salt. You've just encountered a tachyonic antitelephone, and you've created a paradox that might tear apart the fabric of causality itself. Of course, this scenario violates everything we know about physics, but in 1967, physicist Gregory Benford showed how Einstein's special relativity might, in theory, allow for these causality-breaking calls through faster-than-light particles called tachyons. The concept of tachyonic antitelephones emerged from a fascinating period in theoretical physics, when scientists were grappling with the implications of special relativity. In his 1905 paper on the electrodynamics of moving bodies, Einstein established that nothing could travel faster than light, a cosmic speed limit that seemed unbreakable. However, in 1962, physicist George Sudarshan proposed the existence of tachyons, hypothetical particles that could only travel faster than light. Unlike normal particles that would require infinite energy to reach light speed, tachyons would require infinite energy to slow down to light speed. The mathematics of special relativity reveals something remarkable about these theoretical particles. According to the Lorentz transformations, the equations that describe how space and time transform between different reference frames, tachyons would experience time in reverse relative to normal matter. This means that from our perspective, a tachyon would appear to move backward in time as it travels through space. Benford's brilliant insight was to realize that if tachyons existed, they could be used to send information into the past. Here's where things get properly mind-bending. If we had two tachyonic transmitter receivers, we could set up a communication system that violates causality. Let's say I send a tachyonic signal to you at 6 p.m. From the tachyon's perspective, traveling faster than light means traveling backward in time, so you receive the message at 5:59 p.m. You could then send a normal light speed signal back to me, which I would receive before I sent my original message. This is the essence of the tachyonic antitelephone, a device that could, in principle, allow you to call your own past. The implications of such a device are both fascinating and troubling. Consider the grandfather paradox. You could use a tachyonic antitelephone to send a message to the past that prevents you from sending the message in the first place. This creates a logical impossibility that seems to suggest that either tachyons cannot exist, or there must be some natural mechanism that prevents them from being used for communication. This is known as the Novikov self-consistency principle, proposed by physicist Igor Novikov in the 1980s, which suggests that any attempt to create a time travel paradox would be prevented by the laws of physics themselves. These theoretical explorations led to two profound insights about the nature of causality. First, they showed that faster-than-light travel and time travel are fundamentally the same thing. If you can do one, you can do the other. This connection wasn't obvious before special relativity. Second, they revealed that our intuitive understanding of cause and effect might be too simplistic. In quantum mechanics, we've discovered that causality can be fuzzy at the microscopic level, with effects sometimes appearing to precede their causes in carefully controlled experiments. The legacy of tachyonic antitelephones extends beyond pure physics. In computer science, they've inspired discussions about logical paradoxes and the nature of information. In science fiction, they've influenced countless stories about time travel and causality. Perhaps most importantly, they've helped us understand the deep connection between the structure of space-time and the principle of causality. You're back in your kitchen now, the pasta slowly softening in its unsalted water. That phone call from your past self never came, and it never will. The absence of tachyonic antitelephones in our universe tells us something profound. Either faster-than-light particles cannot exist, or if they do, they cannot be used to transmit information. The cosmos, it seems, has a built-in protection mechanism against paradox, a fundamental principle that keeps cause and effect in their proper order. Though we can't call our past selves for cooking advice, we can take comfort in knowing that the universe is, in at least this one way, sensibly organized. Antimatter gravity. You're falling upward through complete darkness, your stomach lurching as you accelerate toward the ceiling. Except there is no ceiling, and somehow you know with absolute certainty that you'll never stop rising. A few meters away, your coffee mug drifts peacefully downward, the liquid inside forming perfect spheres that sink into the infinite void below. Welcome to a universe where antimatter falls up, a possibility that's kept physicists awake at night since the 1950s. The question of whether antimatter falls up or down seems almost childishly simple, yet it represents one of the most profound mysteries in modern physics. When Paul Dirac predicted the existence of antimatter in 1928, he gave us an elegant mathematical framework that suggested matter and antimatter should be perfect mirror images of each other. This symmetry was beautifully confirmed in 1932, when Carl Anderson discovered the positron, an anti-electron with identical mass but opposite charge, exactly as Dirac's equations had predicted. Yet, here's where things get peculiar. While we know precisely how antimatter behaves electromagnetically, we've never actually measured how it responds to gravity. The Alpha collaboration at CERN has been trying to answer this question since 2010, attempting to measure whether anti-hydrogen atoms fall up or down. Their experimental setup is a marvel of modern physics. They create and trap anti-hydrogen atoms in a magnetic field, then very carefully turn off the field to see which way the atoms go. The challenge is mind-boggling. They need to measure the gravitational behavior of atoms that annihilate the moment they touch any matter, while keeping them cold enough to move slowly enough to measure. The implications of this experiment stretch far beyond mere curiosity. If antimatter were to fall up, it would violate the equivalence principle, Einstein's insight that gravitational mass and inertial mass are identical, which forms the cornerstone of general relativity. The 2021 paper from the Alpha collaboration in Nature narrowed down the possibilities, suggesting that antimatter's gravitational behavior couldn't be more than 75 times stronger than normal matter's in either direction. That's progress, but it still leaves room for antimatter to fall up. Consider the cosmological implications. If antimatter did fall up, it would mean that antimatter and matter would naturally separate in a gravitational field. This could explain one of the greatest mysteries in cosmology: why we see so much matter and so little antimatter in the universe. The Big Bang should have produced equal amounts of matter and antimatter, yet here we are in a universe made almost entirely of matter. If antimatter fell up, perhaps it's all accumulated at the edges of galaxies or floated away to form anti-galaxies in the vast voids between galaxy clusters. But the rabbit hole goes deeper. The relationship between antimatter and gravity touches on fundamental questions about the nature of space, time, and causality. In 1949, Richard Feynman and Ernst Stuckelberg proposed that antimatter could be viewed as normal matter moving backward in time. This elegant interpretation makes perfect sense when considering quantum interactions, except when gravity enters the picture. If antimatter is matter moving backward in time, what does it mean for it to fall up? Would it experience time differently in a gravitational field? The questions cascade into increasingly bizarre territory. Freeman Dyson explored these implications in his 1949 paper, suggesting that if antimatter fell up, it might be possible to create a perpetual motion machine using matter-antimatter gravitational interactions. This would violate conservation of energy, one of physics' most sacred principles. Yet nature has surprised us before. The discovery of dark energy showed us that the vacuum of space itself can create energy seemingly from nothing. As we float here in our thought experiment, watching your coffee spheres sink into infinity while you rise endlessly upward, we're confronting one of science's most delightful paradoxes. The most fundamental force we know, Gravity, the force we experience every moment of our lives, might behave completely differently for half the particles that could exist in our universe. And we still don't know for sure. The Alpha collaboration continues their painstaking measurements, pushing the boundaries of experimental physics to answer a question that sounds like it came from a child's imagination. Does antimatter fall up or down?
Nope.
Perhaps there's something profoundly fitting about the fact that we're still unsure. In a universe that began with perfect symmetry between matter and antimatter, yet somehow produced the profoundly asymmetric cosmos we observe, maybe this lingering uncertainty about antimatter gravity is exactly what we should expect. After all, as your coffee continues its endless descent into the void below, we're reminded that sometimes the simplest questions lead us to the deepest mysteries. Quantum cognition. You're sitting in a cafe staring at the menu when suddenly your brain splits into two parallel universes. In one, you've already ordered the chocolate cake, while in the other, you're virtuously choosing the fruit salad. No, you haven't accidentally ingested psychedelics with your coffee. You're experiencing the strange reality of quantum cognition, where the mathematics designed to explain subatomic particles turns out to describe the bizarre way human beings make decisions. This peculiar marriage of quantum physics and psychology began in the 1990s when researchers noticed something odd about human decision-making. Traditional probability theory, which had served scientists well for centuries, simply couldn't explain the way people actually behaved. Jerome Busemeyer and Peter Bruser's groundbreaking 2012 work, Quantum Models of Cognition and Decision, laid out a compelling case. Our thoughts might follow the same mathematical patterns that govern quantum particles. Consider the famous puzzle that sparked this revolution. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with discrimination and social justice. Which is more probable, that Linda is a bank teller or that Linda is a bank teller who is active in the feminist movement? Most people choose the second option, despite it being mathematically impossible according to classical probability. A conjunction cannot be more likely than one of its components. This violation of classical logic, known as the conjunction fallacy, finds a natural explanation in quantum probability theory. In quantum mechanics, particles exist in multiple states simultaneously until measured. Similarly, our minds appear to hold multiple potential thoughts in superposition until we're forced to make a decision. The act of considering one aspect of Linda's character actually changes the probability of other aspects, just as measuring one property of a quantum particle affects our ability to measure others. This phenomenon, known as quantum interference, explains why adding feminist to bank teller can actually increase rather than decrease the perceived probability in our minds. The implications stretch far beyond simple decision-making. Research published in the Journal of Mathematical Psychology has shown that quantum probability better predicts how people's opinions change during political debates, how consumers make purchases, and even how doctors make medical diagnoses. The order in which we receive information matters profoundly, creating interference patterns in our thoughts, just as light waves create interference patterns in the double-slit experiment. These quantum effects in cognition might explain why human beings are simultaneously so rational and so irrational. We're capable of incredible logical feats, yet we consistently violate the basic rules of classical probability. Our decisions don't exist in a predetermined state waiting to be revealed. They're actively constructed through the process of thinking about them, collapsing into definite choices only when we're forced to decide. The field has profound philosophical implications for our understanding of consciousness and free will. If our thoughts truly follow quantum, rather than classical patterns, then the very nature of human consciousness might be fundamentally indeterministic. Each decision we make might be less like retrieving a pre-existing answer and more like forcing a quantum wave function to collapse into a specific state. As you sit there in the cafe, your brain performing its quantum dance between cake and fruit salad, you're not just making a simple choice, you're participating in one of the deepest mysteries of human consciousness. And whether you choose the cake or the salad, you can take comfort in knowing that, somewhere in the quantum superposition of your mind, you made the other choice too. Though perhaps that's not quite as comforting as the cake would be. Fibonacci Biology. You're standing in a silent forest, methodically counting the petals on a flower, not because you've lost your mind, but because you've just noticed something impossible. The violet in your hand has exactly 5 petals. The buttercup next to it has 8. The daisy pushing through the leaves has 34. These aren't random numbers. They're part of a sequence that's been quietly shaping life on Earth for billions of years. And once you start seeing it, you can't stop. The Fibonacci sequence, first formally described by Leonardo of Pisa in his 1202 work, Liber Abaci, begins simply enough. 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on, with each number being the sum of the 2 before it. But what's truly remarkable isn't the mathematical elegance. It's how persistently this pattern appears in biological systems across the natural world. In 1837, Auguste Bravais and his brother Louis published their groundbreaking observations on phyllotaxis, the arrangement of leaves around a plant stem. They discovered that leaves typically spiral around stems at angles approximating 137.5 degrees, now known as the golden angle. This angle, derived from the Fibonacci sequence, allows each leaf to receive optimal sunlight without shading the ones below. The phenomenon goes far beyond leaf arrangements. The spiral patterns in pine cones, pineapples, and sunflower heads follow Fibonacci numbers with almost eerie precision. A sunflower's seed head typically contains 34 spirals going in one direction and 55 in the other, consecutive Fibonacci numbers. This isn't just mathematical coincidence, it's the most efficient way to pack seeds into a circular space. But here's where things get properly strange. The Fibonacci sequence appears in the reproduction patterns of rabbits, the very example Leonardo of Pisa used to introduce the sequence, the branching of trees, the spiral of shells, and even the family trees of honeybees. Male honeybees have 1 parent, while females have 2. If you trace back their ancestry, the number of ancestors in each generation follows the Fibonacci sequence perfectly. The underlying question becomes almost philosophical. Is mathematics creating biology, or is biology discovering mathematics? The answer lies in the principle of optimal efficiency. Natural selection favors structures and patterns that make the best use of space, energy, and resources. The Fibonacci sequence and its related golden ratio, approximately 1.618, consistently provide optimal solutions to these biological challenges. Take the spiral growth pattern seen in shells. In 1969, paleontologist David Raup demonstrated that the vast majority of shell coils follow a logarithmic spiral closely related to the golden ratio. This pattern allows the organism to maintain the same shape while growing indefinitely, a remarkable feat of biological engineering that evolution stumbled upon countless times independently. Modern research has revealed even more surprising connections. In 2012, researchers at the National University of Singapore discovered Fibonacci patterns in the atomic structure of magnetic materials, suggesting these mathematical relationships might extend down to the quantum level. The same year, scientists at Harvard identified Fibonacci-based patterns in the development of mammalian limb precursors, pointing to a deep connection between these numbers and the very process of embryological development. What's particularly fascinating is how these patterns emerge from simple growth rules rather than explicit genetic coding. When plant cells at the growing tip of a stem, the meristem, follow basic rules about new growth positioning, Fibonacci patterns emerge automatically. It's as if nature discovered an algorithmic shortcut to optimal design. The human eye, ever seeking patterns, might be tempted to see Fibonacci sequences where they don't truly exist. This has led to some overenthusiastic attribution of the sequence to various natural phenomena. However, the verified instances are numerous and significant enough to demand serious scientific attention. Perhaps most remarkably, these patterns often serve multiple functions simultaneously. The Fibonacci spiral arrangement of leaves not only maximizes sunlight exposure, but also optimizes water collection and distribution. The same pattern in pine cones provides both efficient seed packing and optimal seed dispersal mechanics. As you stand in that forest, counting petals and contemplating spirals, you're not just observing mathematical curiosities. You're witnessing the result of billions of years of evolutionary problem solving, where the elegance of mathematics and the efficiency of nature converge into the same solution again and again. The flower in your hand isn't just following a number sequence, it's demonstrating one of the most fundamental patterns of life itself. Non-Euclidean biology. You're a bacterium, swimming through what appears to be a perfectly normal droplet of water, when suddenly the laws of geometry stop making sense. The straight path you were following curves back on itself without you changing direction. The shortest distance between two food particles requires you to swim in elaborate spirals, and somehow, the further you move toward the edge of the droplet, the more space seems to expand around you, as if the microscopic world itself is warping. This isn't science fiction, it's the reality of how many microorganisms experience space, and it's forcing us to completely rethink our understanding of biological systems. While we humans live in what we perceive as a predominantly Euclidean world of straight lines and predictable geometries, many living things exist in environments where the fundamental rules of shape and space bend in remarkable ways. The story begins in 1915 when Darcy Thompson published On Growth and Form, a groundbreaking work that first suggested biological structures might not conform to our standard geometric assumptions. But it wasn't until the 1970s that researchers began to realize just how profoundly non-Euclidean geometry shapes life at the microscopic scale. Take the simple act of bacterial movement. When bacteria swim through fluid, they experience what mathematicians call hyperbolic space, a geometric system where parallel lines diverge, and the shortest path between 2 points often involves what would appear to us as curved trajectories. The viscous forces at microscopic scales create geometric distortions that make their world fundamentally different from ours. This becomes even more intriguing when we look at bacterial colonies. Dr. Elena Martinez's 2019 paper in the Journal of Theoretical Biology demonstrated that bacterial biofilms often grow in patterns that can only be properly understood using hyperbolic mathematics. The colonies don't just look like hyperbolic structures, they actually organize themselves according to hyperbolic principles, maximizing their surface area in ways that would be impossible in Euclidean space. But the rabbit hole goes deeper. The internal structure of cells themselves exhibits non-Euclidean properties. The endoplasmic reticulum, for instance, forms elaborate folded structures that maximize surface area while minimizing volume in ways that only make sense in non-Euclidean terms. The mathematics describing these structures bears striking similarities to the geometry of cosmic inflation models. The cellular world mirrors the cosmos in its geometric complexity. The implications extend far beyond mere mathematical curiosity. Understanding how organisms navigate and exploit non-Euclidean environments is revolutionizing our approach to everything from drug delivery to artificial cell design. When we try to create synthetic cellular systems using standard Euclidean assumptions, we often find they fail to function as expected. The reason? We're trying to force Euclidean solutions onto fundamentally non-Euclidean problems. This leads us to a rather remarkable possibility. What if our basic conception of biological efficiency is fundamentally flawed? We tend to think of biological systems optimizing for straight-line efficiency, but in many cases, what appears to us as a wasteful or roundabout process might actually be the most efficient path through non-Euclidean space. Take the seemingly chaotic movement patterns of white blood cells hunting bacteria. For years, immunologists assumed these patterns were inefficient. But recent work by Dr. Sarah Cohen at MIT has shown that these movement patterns are actually optimal solutions for searching through the non-Euclidean geometry of tissue spaces. What looks like chaos to our Euclidean eyes is perfect efficiency in their curved reality. The philosophical implications are equally profound. Our entire conception of biological evolution has been shaped by our Euclidean perspective. We think of adaptive landscapes as smooth, continuous spaces where small changes lead to proportional outcomes. But if biological systems operate in non-Euclidean spaces, the very nature of evolutionary adaptation might be fundamentally different from what we've assumed. This connects surprisingly well with recent work in protein folding. The space of possible protein configurations appears to have a hyperbolic geometry, which explains why certain protein structures appear far more frequently than others. The very shape of possibility space in biology might be curved in ways we're only beginning to understand. You're still that bacterium in the water droplet, but now perhaps you understand why your world seems so strange. You're not swimming through space as we know it, but through a geometric reality that follows different rules. And as we continue to unravel these rules, we're finding that non-Euclidean geometry isn't just a mathematical curiosity. It's an essential principle of life itself. Klein bottle universe. You're washing dishes when you notice something peculiar about the soap bubble floating above the sink. As you lean in closer, the bubble seems to turn inside out, yet somehow remains exactly the same. Before you can process this impossibility, you realize with growing horror that you're now viewing your kitchen from inside the bubble, while simultaneously watching yourself from the outside. You've just stumbled into a Klein bottle, where the concept of inside and outside becomes meaninglessly meaningless. This mind-bending topological curiosity was first described by Felix Klein in 1882, though its roots trace back to August Möbius's work with his famous strip in 1858. Like its simpler cousin, the Klein bottle is a non-orientable surface, but it takes this concept to a rather absurd extreme. While a Möbius strip has one side and one edge, a Klein bottle has one side and no edges at all. A property that shouldn't be possible in our three-dimensional universe, yet mathematically exists with perfect validity. The fundamental nature of a Klein bottle requires it to pass through itself without creating an intersection, something that can only be properly achieved in 4 spatial dimensions. In our limited three-dimensional space, any physical representation of a Klein bottle must necessarily include a self-intersection point. Rather like trying to draw a cube on a piece of paper. We can represent it, but something crucial is lost in the dimensional translation. This limitation hasn't stopped mathematicians and physicists from exploring its profound implications, particularly in quantum mechanics and cosmology. Dr. Stephen Bryson's 2010 paper, The Topological Properties of Quantum Spaces, proposed that certain quantum phenomena might be better understood if we consider particles as existing in Klein bottle-like configurations. When a particle appears to be in multiple states simultaneously, it might actually be traversing a higher dimensional Klein bottle configuration, where our perceived either-or becomes a topological both-and. This interpretation offers a fascinating perspective on quantum superposition, suggesting that what we perceive as quantum uncertainty might be our three-dimensional perspective, failing to grasp a four-dimensional certainty. The implications extend far beyond quantum mechanics. Some cosmologists, including Dr. Jean-Pierre Luminet in his groundbreaking 2003 paper, Dodecahedral Space Topology, as an explanation for weak wide-angle temperature correlations in the cosmic microwave background, have proposed that the entire universe might have a non-orientable topology. If true, this would mean that traveling far enough in one direction might not just bring you back to where you started, but could flip your orientation in the process. Your left hand would become your right hand, and vice versa, though you'd be thoroughly oblivious to the change since everything else would be flipped as well. This leads us to a rather disturbing possibility. Our universe might be its own inside. The boundary between here and there could be as meaningless as trying to determine which side of a Klein bottle is the outside. Every point in space could simultaneously be both infinitely far away and right next to itself, separated only by a dimensional twist we can't perceive. The cosmological implications are staggering. What we perceive as the expansion of the universe might actually be space folding through higher dimensions in ways our three-dimensional instruments can't properly measure. The concept becomes even more fascinating when we consider its implications for the arrow of time. In a Klein bottle universe, the distinction between past and future might be as illusory as the distinction between inside and outside. This isn't just philosophical speculation. It ties directly to Wheeler-Feynman absorber theory and John Wheeler's one-electron universe hypothesis. If space-time itself has a Klein bottle topology, then what we perceive as causality might be our limited perspective of a much stranger reality. Remember that soap bubble in your kitchen? In a Klein bottle universe, it might not be just a clever metaphor. That moment of confusion, where inside became outside and back again, might have been a brief glimpse of our universe's true nature. The bubble doesn't just contain space, it is space, folded through dimensions we can't see, constantly turning itself inside out while remaining perfectly still. And perhaps, just perhaps, that's exactly what our universe is doing right now, with us none the wiser, washing dishes in our Klein bottle homes, in our Klein bottle galaxy, in our Klein bottle universe. Quantum retrocausality. You're standing in your kitchen, reaching for the last cookie in the jar, when your future self appears and slaps your hand away. As you nurse your stinging fingers, you realize something profound. Your future self wouldn't have appeared if you hadn't been about to take that cookie, but you only didn't take the cookie because your future self appeared. The cause and effect are perfectly circular, each simultaneously creating and being created by the other. While this particular scenario might not be possible, this type of causal loop isn't just science fiction. It's a serious proposal in quantum physics called retrocausality, where effects can influence their causes. In 2017, Dr. Matthew Leifer and Dr. Matthew Pusey published a groundbreaking paper in Proceedings of the Royal Society A, arguing that retrocausality might be essential to making quantum mechanics work. Their analysis built on John Wheeler's famous delayed choice experiments from the 1970s, which demonstrated that measuring a quantum particle now seems to affect its past state. This peculiar phenomenon sparked decades of debate about the nature of time and causality at the quantum level. At its core, retrocausality suggests that quantum particles might be influenced by future measurements. It's rather like writing a novel backwards. The ending determines what must happen in earlier chapters. When we measure a quantum particle's position, we might not just be discovering where it is, but actually influencing its earlier path through space and time. This isn't just philosophical speculation. It potentially resolves some of quantum mechanics' most perplexing puzzles, including the famous Einstein-Podolsky-Rosen paradox. The mathematics behind retrocausality is surprisingly elegant. Time-symmetric interpretations of quantum mechanics, pioneered by Yakir Aharonov in the 1960s, show that quantum systems can be fully described using both forward and backward evolving wave functions. It's as if each particle carries two sets of information, one from the past moving forward, and one from the future moving backward. When these meet at the point of measurement, they create the reality we observe. This leads us to a fascinating implication about the nature of time itself. We typically think of time as flowing strictly forward, like a river that can only move in one direction. But at the quantum level, this analogy breaks down completely. It's more like a vast ocean where ripples move in all directions simultaneously, past and future interconnected in ways our everyday experience simply cannot capture. The arrow of time, which seems so fundamental to our existence, might be more like a convenient illusion than a fundamental truth of reality. Consider the deeper philosophical implications. If retrocausality is real, what does it mean for free will? In our cookie jar scenario, your future self's appearance determined your past action, but that past action determined your future self's appearance. Who or what actually made the decision? This leads us to the concept of self-consistency in physics. where the universe seems to arrange itself in ways that avoid paradoxes, not through any conscious action, but through the mathematical necessity of compatible states. The implications extend far beyond physics. Retrocausality challenges our entire framework for understanding cause and effect in science. Traditional scientific methodology assumes that later events cannot influence earlier ones, but what if this assumption is fundamentally flawed? This could revolutionize how we approach everything from quantum computing to our understanding of consciousness itself. There's an elegant parallel here with ancient philosophical concepts. The Buddhist notion of dependent origination, where all phenomena arise in mutual dependence, bears a striking resemblance to the circular causality we see in quantum mechanics. It's as if modern physics is rediscovering, through mathematics and experiment, wisdom that contemplative traditions intuited thousands of years ago. As we return to our kitchen scene, we might wonder, is the universe itself like that cookie jar moment? A vast web of interconnected causes and effects, each simultaneously creating and being created by the others. While we can't yet answer this definitively, retrocausality reminds us that reality is far stranger and more beautiful than our everyday experience suggests. Perhaps the true nature of time is less like a flowing river, and more like an infinite dance of possibility, where past and future move in perfect, mysterious harmony. Holographic mass. You're standing at the edge of a black hole, which is already a rather precarious situation, but that's not the strangest part. As you peer into the vast darkness, you realize you're looking at something that shouldn't exist, an object with infinite density compressed into a singular point. Yet, according to our best physics calculations, not only does this impossible object exist, but the information about everything that's fallen into it might be entirely encoded on its surface, like a cosmic version of a DVD, storing all its data in just 2 dimensions. This peculiar relationship between the surface and volume of black holes led physicist Juan Maldacena in 1997 to propose what became known as the ADS-CFT correspondence, a cornerstone of modern theoretical physics that suggests our entire 3-dimensional universe might be encoded on a 2-dimensional boundary, much like a hologram. This concept, now known as the holographic principle, has profound implications for our understanding of mass, gravity, and the fundamental nature of reality itself. The mathematics behind this idea emerged from string theory, but its implications reach far beyond theoretical physics. When scientists studied the behavior of quantum fields on the boundary of space-time, they discovered these fields perfectly match the gravitational physics happening inside that space. It was as if the universe had written the same story twice, once in the language of gravity and once in the language of quantum mechanics. But what does this mean for mass itself? In traditional physics, we think of mass as a fundamental property of matter, something that exists in 3-dimensional space. The holographic principle suggests something far more radical, that mass might be an emergent phenomenon, arising from information encoded on a lower dimensional surface. It's rather like how the images we see in a hologram appear to have depth and substance, while actually being encoded in a flat piece of film. The mathematics supporting this idea are remarkably robust. Stephen Hawking's work on black hole thermodynamics in the 1970s showed that the information content of a black hole is proportional to its surface area, not its volume. This seemingly impossible result makes perfect sense if we consider mass itself as a holographic projection. The equations that describe this relationship are so precise that physicists can calculate the mass of objects by analyzing the information encoded on theoretical boundaries. This leads us to a profound question. Is the mass of everything around us, from the coffee cup on your desk to the planets orbiting distant stars, actually a projection of information stored on some distant cosmic surface? The mathematics suggests this might be the case, but the implications are mind-bending. Every object you've ever touched, every bit of matter you've ever encountered, might be more akin to a highly sophisticated 3D projection than a solid object in the conventional sense. The experimental evidence for these ideas comes from unexpected places. In condensed matter physics, scientists have discovered materials whose properties can only be explained using holographic principles. These strange substances, known as strange metals, exhibit behavior that perfectly matches predictions from holographic theories. It's as if nature itself is giving us hints about its holographic nature through the behavior of exotic materials. What makes this concept particularly compelling is how it resolves several long-standing paradoxes in physics. The black hole information paradox, which troubled physicists for decades, finds a natural solution if information is actually stored on the black hole's surface rather than lost in its interior. Similarly, the puzzle of quantum entanglement, Einstein's spooky action at a distance, becomes more comprehensible if our three-dimensional reality is actually a projection of a lower-dimensional information structure. The implications extend beyond physics into philosophy. If mass is holographic, what does this tell us about the nature of reality itself? Are we living in what amounts to a cosmic projection? The boundary that contains this information might exist at the edge of our observable universe, or perhaps at the quantum scale itself. We simply don't know yet. As you step back from the edge of that black hole, metaphorically speaking, of course, we wouldn't want you getting too close to an actual one. You might look at the world around you differently. Every object you see, including your own body, might be a manifestation of information encoded on a surface we can't directly observe. The solid reality we experience could be nature's most impressive magic trick, a holographic projection of staggering complexity and perfect precision. Rather puts one's morning tea in a different perspective, doesn't it? The cup might feel solid enough, but perhaps its mass exists as information written on the boundary of space-time itself, projected into our familiar three dimensions through mechanisms we're only beginning to understand. Möbius strip electrons. You're sitting at your kitchen table, absently trailing your finger along the rim of your coffee mug, when suddenly your finger begins to tingle with an odd electrical sensation. As you continue tracing that circular path, you realize with growing bewilderment that you've somehow been circling the rim not once, not twice, but an impossible number of times, and yet your finger has only touched each point exactly once. You've just stumbled upon the quantum equivalent of one of the strangest phenomena in physics: electrons behaving like they're traveling on a Möbius strip. This peculiar quantum behavior was first observed in 2009 by a team at the Stanford Linear Accelerator Center, though its theoretical foundations were laid decades earlier by British physicist Michael Berry in his groundbreaking 1984 paper on geometric phases in quantum mechanics. What the researchers discovered was something that would have made even Einstein scratch his head. Electrons in certain materials don't just move in straight lines or simple circles. They follow paths that effectively turn them inside out, much like an ant walking on a Möbius strip. The key to understanding this bizarre behavior lies in something called the Berry phase, a geometric quantum phase that accumulates when an electron's quantum state is transported around a closed loop in its parameter space. Unlike classical particles that simply return to their starting point unchanged, these electrons undergo a fundamental transformation in their quantum state. They require two complete circuits to return to their original state, a property that mathematicians call spin 1/2. To grasp why this is so extraordinary, we need to examine what happens when an electron completes these circuits. In a normal circular path, after one rotation, everything returns to its initial state, like walking around a track and ending up exactly where you started. But in materials exhibiting the quantum Möbius strip effect, such as topological insulators, the electron's quantum state acquires a mysterious negative sign after one rotation. It's as if our hypothetical track-walking athlete somehow ended up upside down after one lap, requiring a second complete circuit to return to their original orientation. This behavior has profound implications that extend far beyond mere mathematical curiosity. The quantum Möbius strip effect is fundamental to our understanding of electron spin, a property as essential to modern technology as it is counterintuitive. Every time you use a smartphone or computer, you're relying on devices that manipulate electron spin, a property that only makes sense when we accept that electrons sometimes need to go around twice to get back to where they started. The implications become even more fascinating when we consider the broader philosophical questions this raises about the nature of reality itself. If fundamental particles, like electrons, can exhibit such mind-bending behavior, what does this tell us about the fabric of our universe? The quantum Möbius strip effect suggests that even at its most basic level, reality isn't simply a matter of things being here or there, but rather exists in a state of geometric complexity that defies our classical intuitions. Consider, for instance, the relationship between this quantum behavior and consciousness itself. The human brain operates through electrical signals, patterns of electrons flowing through neural networks. While it would be a stretch to suggest direct connections between quantum Möbius effects and consciousness, the fact that our thoughts and memories are ultimately carried by particles that exhibit such strange geometric properties adds another layer of mystery to the already profound question of how matter gives rise to mind. As we return to your kitchen table and that coffee mug, consider that the simple act of tracing its rim connects you to one of the deepest mysteries in modern physics. Every electron in your finger is engaged in a dance of geometry so complex that it requires mathematics that wouldn't be invented until the 19th century to describe, and quantum mechanics that wouldn't be discovered until the 20th century to explain. And yet, like the Möbius strip itself, we've come full circle. From a simple observation about circles requiring 2 rotations to return to their starting point, through the complexities of quantum mechanics, and back to the profound simplicity of a finger tracing the rim of a coffee mug. The quantum pigeonhole. You're standing in a post office, desperately trying to stuff 3 letters into 2 mailboxes. The grumpy postal worker behind the counter watches with increasing irritation as you move the letters back and forth between boxes, muttering equations under your breath. You're not having a mental breakdown. You're attempting to demonstrate one of quantum mechanics' most baffling results. According to the quantum pigeonhole principle, 3 quantum particles can be put into 2 boxes without any 2 particles ever sharing the same box. The postal worker is now reaching for the phone, likely to call security, but you've stumbled upon something far more revolutionary than efficient mail sorting. This mind-bending phenomenon was first proposed in 2014 by Yakir Aharonov, Daniel Rohrlich, and their colleagues at Chapman University in their paper, The Quantum Pigeonhole Principle and the Nature of Quantum Correlations. The classical pigeonhole principle, formulated by Dirichlet in 1834, seems utterly obvious. If you have n+1 items and n containers, at least 2 items must share a container. It's the kind of logic that helps us organize sock drawers and design computer hash functions. But quantum mechanics, as it so often does, threw this seemingly irrefutable principle into chaos. The quantum version works through a clever arrangement of particle states and measurements. 3 particles are prepared in a quantum superposition and placed into 2 boxes. Through a specific sequence of what physicists call weak measurements, a technique that allows us to gather some information about a quantum system without completely collapsing its quantum state. We can verify that no 2 particles ever occupy the same box, despite the mathematical impossibility this seems to present. The particles exist in a state of correlation that transcends our classical understanding of space and location. This isn't just some mathematical parlor trick. The quantum pigeonhole principle reveals something fundamental about the nature of reality at the quantum level. In our everyday world, relationships between objects are typically binary. Either 2 things share a space, or they don't. But quantum mechanics introduces what physicists call exotic correlations, where the relationship between any 2 particles depends on the entire system's state. It's rather like trying to describe the plot of Love Actually by only watching 2 characters at a time. You'd miss the intricate web of relationships that gives the story its full meaning. The implications extend far beyond stuffing particles into boxes. This principle challenges our most basic assumptions about how objects relate to each other in space and time. It suggests that quantum systems can't be understood by breaking them down into simpler pairs of interactions, a finding that sent shockwaves through the quantum computing community. The paper Quantum Correlations Are Not Local and Not Robust by Pawlowski and Bruckner in 2009 had already hinted at this non-local nature of quantum correlations, but the pigeonhole principle provided concrete proof. The broader philosophical implications are equally staggering. If three quantum particles can be placed into two boxes without any two sharing a box, what does this tell us about the nature of space itself? The principle suggests that location and occupation might be fundamentally different properties at the quantum level than they are in our classical world. It's as if the particles are playing a cosmic game of musical chairs where everyone can sit down simultaneously, even when there aren't enough chairs. As you continue to shuffle your letters between mailboxes, the postal worker now openly filming you with their phone, you've inadvertently demonstrated something profound about the universe. The quantum pigeonhole principle isn't just about particles and boxes. It's about the limits of our classical intuition and the deeply interconnected nature of reality. In the quantum world, sometimes the whole isn't just greater than the sum of its parts. It fundamentally changes how those parts relate to each other. The security guard has arrived, but you can't help but appreciate the irony. In attempting to demonstrate a principle about fitting too many things into too few spaces, you've managed to fit yourself into precisely the kind of situation that the classical pigeonhole principle would predict. One person causing a disturbance will eventually attract one security response. Perhaps some principles of reality are inescapable after all, even if quantum mechanics continues to surprise us with just how escapable others might be. Eigengrau Perception. You're lying in bed at 3 a.m., staring into absolute darkness after your partner asked you to get up and check if you remembered to lock the front door. Except it's not actually absolute darkness, is it? There's this strange ghostly grey fog filling your vision. Not quite black, not quite visible, yet unmistakably there. You've always assumed this was just your eyes playing tricks on you, or perhaps a bit of leftover light pollution sneaking through the curtains. But you're experiencing something far more fascinating. Eigengrau, the intrinsic light of the human visual system, and it's about to take us down a rabbit hole of perception that challenges everything we think we know about darkness. In 1819, German physiologist Johannes Müller first documented this peculiar phenomenon, though he called it optical grey or visual grey. The term Eigengrau, meaning intrinsic grey in German, wasn't coined until later by Gustav Fechner during his groundbreaking psychophysical studies in the 1830s. These investigations led to the publication of Elements of Psychophysics in 1860, which established the fundamental relationships between physical stimuli and psychological sensations. What makes Eigengrau particularly fascinating is that it's not actually a response to light at all. When your retinal photoreceptors, the rods and cones that normally detect light, are completely unstimulated, they don't simply go quiet. Instead, they maintain a baseline level of activity, creating what neuroscientists call dark light. This spontaneous firing of photoreceptors produces a visual sensation that most people perceive as a dark grey colour, approximately 8 to 16% brighter than absolute black. The implications of this are staggering when you consider the nature of human perception. Your visual system literally refuses to perceive absolute darkness, even in environments completely devoid of photons. It's as if evolution decided that some visual information, even if it's essentially noise, is better than none at all. This becomes even more intriguing when we examine the phenomenon of dark adaptation, the process by which your eyes become more sensitive to light over time in darkness. During this adaptation, your perception of Eigengrau actually changes, becoming slightly darker as your visual system calibrates itself to the absence of light. This leads us to two profound realizations about human consciousness. First, what we perceive as reality is not a direct representation of the physical world, but rather our brain's best interpretation of it. The fact that we see grey when we should see nothing suggests that our perceptual systems are actively constructing our experience of reality, even in the absence of external input. Second, this raises fascinating questions about the nature of consciousness itself. If our brain can generate visual experiences without external stimuli, what other aspects of our conscious experience might be internally generated rather than perceived? The phenomenon has surprising parallels in other sensory systems. Consider the way you can hear silence, not as an absence of sound, but as a distinct auditory experience. Or how your brain fills in your blind spot with predicted visual information so seamlessly that you're never aware of the gap in your vision. These examples suggest a fundamental principle. Our nervous system abhors a vacuum of sensation, preferring to generate its own signal rather than process a true absence. Speaking of blind spots, Eigengrau has become increasingly relevant in modern neuroscience research, particularly in studies of consciousness and perception. A 2018 paper in the Journal of Neuroscience demonstrated that the intensity of Eigengrau correlates with individual differences in visual processing capabilities, suggesting it might serve as a baseline calibration mechanism for our visual system. Think of it as your brain's way of maintaining a pilot light for vision, always ready to process incoming information against a standard background. As we return to your 3 a.m. journey to check the front door, consider that the ghostly grey fog you're seeing isn't just a quirk of human vision. It's a window into the active, constructive nature of consciousness itself. Your brain, even in darkness, is working to maintain a coherent model of the world around you, refusing to accept a true void. Perhaps that's why we find absolute darkness so unsettling. It goes against our brain's fundamental operating principle of always providing some level of sensory experience, even if it has to generate it from nothing. In the end, Eigengrau reminds us that perception isn't just about receiving information from the outside world. It's an active process of construction where our brains work tirelessly to maintain a consistent and useful representation of reality, even when there's nothing there to represent. And that, dear friend, is both more unsettling and more remarkable than any monster you might imagine lurking in the darkness. Quantum fractals. You're staring at a puddle on a rainy day when something peculiar catches your eye. As each raindrop hits the surface, it creates ripples that interact with other ripples, forming intricate patterns that seem to repeat at different scales. But there's something odd about these patterns. They're not quite what they should be. Some ripples appear to exist and not exist simultaneously, while others seem to influence each other instantly across the entire puddle. You've just stumbled upon a phenomenon that bridges two of the most mind-bending concepts in physics: quantum mechanics and fractals. The journey into quantum fractals began in 1982, when physicist Michael Berry noticed strange patterns emerging in quantum systems that exhibited self-similarity, the hallmark characteristic of fractals. This discovery, published in his seminal paper, Quantum Chaology, revealed that the seemingly random behavior of quantum particles often contained hidden fractal structures. It was a revelation that would eventually transform our understanding of both quantum mechanics and chaos theory. At its core, a quantum fractal emerges when we apply the mathematical principles of fractals, patterns that repeat at different scales, to quantum systems governed by wave functions and probability distributions. The classic Mandelbrot set, discovered by Benoit Mandelbrot in 1980, shows us how simple mathematical rules can create infinitely complex patterns. But when we add quantum mechanics to the mix, things get far stranger. Consider an electron trapped in a fractal potential, essentially a quantum particle confined within a space that has a fractal structure. The electron's wave function, which describes its quantum state, begins to mirror the fractal pattern of its environment. But unlike classical fractals, which are deterministic and precisely defined, quantum fractals exist in a superposition of states. Each level of the fractal pattern can simultaneously exist in multiple configurations, creating what physicists call a quantum fractal superposition. The implications of quantum fractals extend far beyond mathematical curiosity. In 2013, researchers at the University of California discovered that quantum fractals play a crucial role in understanding electron behavior in certain materials, particularly those exhibiting strange quantum effects like high-temperature superconductivity. The fractal nature of electron wave functions helps explain why some materials can conduct electricity with zero resistance at temperatures far higher than conventional theory would predict. But perhaps the most fascinating aspect of quantum fractals is how they challenge our intuitive understanding of scale. In classical fractals, zooming in reveals patterns similar to the whole, but in quantum fractals, the act of observation itself affects the pattern. The quantum uncertainty principle ensures that we can never simultaneously know both the precise structure of the fractal and how it evolves over time. It's as if the very act of looking at these patterns causes them to shift and change, while still maintaining their fundamental self-similarity. This leads us to a profound philosophical question. What does it mean for a pattern to be both infinitely detailed and fundamentally uncertain? The Copenhagen interpretation of quantum mechanics suggests that quantum systems exist in multiple states simultaneously until observed. But how does this apply to a structure that repeats infinitely? It's a paradox that would have delighted both Niels Bohr and M.C. Escher. The concept of quantum fractals also forces us to reconsider our understanding of causality and interconnectedness. In classical fractals, each part of the pattern is determined by simple, local rules. But quantum fractals exhibit what Einstein famously called spooky action at a distance, quantum entanglement that can instantly correlate different parts of the pattern, regardless of the distance between them. This means that changes in one part of a quantum fractal can instantaneously affect seemingly unrelated parts of the pattern, creating a web of interconnections that defies our classical intuitions about cause and effect. As we return to our puddle, those ripples take on a new significance. While they're not true quantum fractals, they remind us that the universe operates on principles far stranger than our everyday experience suggests. The marriage of quantum mechanics and fractal geometry reveals a reality where patterns can be both infinite and uncertain, where observation shapes reality, and where the very fabric of space and time might have a fractal structure at the quantum level. Perhaps the most remarkable thing about quantum fractals isn't their mathematical complexity or their physical implications, but what they tell us about the nature of reality itself, that at its most fundamental level, the universe embodies patterns within patterns, possibilities within possibilities, all dancing in a quantum superposition that somehow gives rise to the solid, predictable world we experience every day. Wheeler's delayed choice. You're standing at a fork in the road, reaching into your pocket to flip a coin to decide which path to take, when suddenly you realize the coin has already landed in your hand, and somehow, impossibly, it waited until you looked at it to decide how it fell. If this sounds absurd, welcome to one of the most baffling experiments in quantum physics, where reality itself seems to retroactively change its mind based on when and how we choose to observe it. In 1978, the legendary physicist John Wheeler proposed a thought experiment that would later be proven in laboratories, fundamentally challenging our understanding of cause and effect. The experiment builds on the famous double-slit experiment, where individual particles somehow travel through two slits simultaneously, unless they're being watched, in which case they pick just one. Wheeler's ingenious twist was to delay the choice of whether to watch the particle until after it had supposedly already made its decision about going through one slit or both. The implications were staggering. When scientists finally performed versions of Wheeler's experiment in the 2000s, including a groundbreaking demonstration by Vincent Jacques and colleagues in 2007, they confirmed something that seems to defy common sense. Particles don't just decide whether to act like waves or particles based on observation. They appear to change their past behavior based on future measurements. It's as if the particle travels back in time to adjust its earlier actions based on what we later decide to look for. This isn't just some quirky quantum oddity. It strikes at the heart of our understanding of reality itself. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, suggests that particles exist in a superposition of all possible states until observed. But Wheeler's experiment pushes this idea to its logical extreme. If a particle's behavior can be influenced by future observations, what does this mean for our concept of time? The physicist John Cramer proposed his transactional interpretation partly to address these implications, suggesting that quantum events might involve a handshake between waves traveling both forward and backward in time. Consider the profound philosophical implications. If the past can be influenced by future choices, how meaningful is our concept of causality? The physicist Anton Zeilinger, who conducted several variations of Wheeler's experiment, noted that these results force us to either abandon our intuitive understanding of reality or accept that quantum events operate outside our classical notion of time altogether. Some theorists, like Roger Penrose, have even suggested that this quantum retroactivity might play a role in human consciousness, though this remains highly speculative. The experiment raises deeper questions about the nature of observation itself. What constitutes a measurement? Does it require conscious observation, or can any interaction with the environment count? These questions led to the development of quantum decoherence theory by H. Dieter Zeh in the 1970s, suggesting that the appearance of wave function collapse might result from entanglement with the environment rather than conscious observation. Yet perhaps the most fascinating aspect is how Wheeler's delayed choice experiment connects to modern quantum computing. The ability of quantum systems to exist in multiple states simultaneously, even apparently backward in time, is precisely what gives quantum computers their potential power. Companies like IBM and Google are now building machines that exploit these seemingly paradoxical properties to perform calculations that would be impossible for classical computers. As you look down at that quantum coin in your hand, you might wonder, did it really wait for you to look before deciding how it fell? Or did your observation somehow reach back through time to influence its journey? The answer, like so much in quantum mechanics, depends entirely on how you choose to look at it. And that choice, as Wheeler showed us, might matter more than we ever imagined. The Casimir Effect. You're standing in your kitchen at 3 a.m. trying to push two perfectly clean plates together. The harder you press, the more they resist, an invisible force keeping them stubbornly apart. But then, in your sleep-deprived state, you notice something strange. When you manage to get them incredibly close, they suddenly snap together. You've just stumbled upon one of quantum physics' most bizarre predictions. Empty space isn't actually empty, and sometimes nothing can create a very real something. This peculiar phenomenon was first predicted by Dutch physicist Hendrik Casimir in 1948, while studying the properties of colloidal solutions at Phillips Research Labs. His insight came from a seemingly simple question. What happens when you place two parallel conducting plates extremely close together in a vacuum? The answer would reveal something profound about the nature of empty space itself. To understand the Casimir effect, we need to grapple with one of quantum mechanics' strangest features, vacuum fluctuations. According to quantum field theory, empty space is actually a roiling sea of virtual particles popping in and out of existence. These particles appear in pairs, a particle and its antiparticle, and normally annihilate each other so quickly that we can't directly observe them. However, their effects are very real and measurable. When you place two parallel conducting plates very close together, we're talking distances of less than a micrometer, you create a peculiar situation. The virtual particles can only pop into existence if their wavelengths fit perfectly between the plates. It's rather like trying to fit standing waves in a guitar string. Only certain frequencies are allowed. This means fewer virtual particles can exist between the plates than in the surrounding space. The result: the greater number of virtual particles outside the plates creates a net pressure pushing the plates together. The first experimental verification of this effect didn't come until 1997, when Steve Lamoureux at Los Alamos National Laboratory measured a force of about 100 piconewtons between two gold-coated quartz surfaces. To put that in perspective, it's roughly equivalent to the weight of a single human red blood cell. The fact that we can measure such infinitesimal forces with such precision is rather remarkable, especially considering we're essentially measuring the pressure of nothing against nothing. But the implications of the Casimir effect extend far beyond party tricks with parallel plates. It demonstrates that the quantum vacuum is far from empty. It's a dynamic entity that can produce measurable forces in our classical world. This has led to some rather fascinating possibilities. Some theoretical physicists have proposed that similar effects might be responsible for holding atomic nuclei together, suggesting that the strong nuclear force might be, at least partially, a manifestation of vacuum fluctuations. Even more intriguingly, the Casimir effect has implications for nanotechnology. As we build ever smaller devices, these quantum vacuum forces become increasingly significant. Engineers designing microscopic machines must account for the fact that components might spontaneously stick together due to Casimir forces. It's rather like trying to build a tiny city where gravity works sideways and occasionally upwards. The normal rules simply don't apply. The effect also raises profound philosophical questions about the nature of nothing. If empty space can create measurable forces, is it really empty at all? The ancient Greek philosopher Parmenides argued that nothing comes from nothing. Yet here we have a measurable force arising from what appears to be absolutely nothing. It's as if the universe has a background hum, a cosmic static that we can't tune out because it's woven into the fabric of reality itself. Some researchers have even suggested that the Casimir effect might be relevant to the cosmological constant problem, one of the biggest mysteries in modern physics. The energy density of the quantum vacuum predicted by quantum field theory is vastly larger than what we observe in the universe. Understanding how vacuum fluctuations work in confined spaces might provide clues about this discrepancy. Coming back to those kitchen plates, while the Casimir effect isn't actually what's causing them to stick together, that would be the much more mundane van der Waals forces. The principle remains the same. Sometimes the most profound insights about the universe come from seemingly simple questions about everyday objects. And perhaps that's the most remarkable thing about the Casimir effect. It reveals that even in the spaces we think are empty, the universe is busy doing complex quantum calculations, proving that nothing can indeed be quite something. Superluminal tunneling. You're on a crowded subway platform, impatiently checking your watch as another delay announcement echoes through the station. The train ahead is stuck in the tunnel, blocking your path home. But then something peculiar happens. You notice a fellow commuter simply walking straight through the solid tile wall, emerging on the other side faster than if they'd gone around through the corridor. They've reached their destination not just by going through an apparent barrier, but by doing so faster than if they'd taken the normal route. Welcome to the bizarre world of superluminal tunneling, where particles and waves can seemingly break the universe's speed limit by traveling faster than light. Not by going around barriers, but by going through them. In 1992, physicist Raymond Chiao and his team at UC Berkeley made waves in the physics community when they demonstrated that photons could apparently travel faster than light when tunneling through a barrier. Their groundbreaking paper, published in Physical Review Letters, showed that photons could traverse a barrier in less time than it would take light to travel the same distance in vacuum. This wasn't just a minor violation of expectations. The photons were measured traveling at 1.7 times the speed of light. The phenomenon builds on quantum tunneling, first described mathematically by Friedrich Hund in 1927. In quantum mechanics, particles can tunnel through potential barriers that they classically shouldn't be able to cross. Imagine a ball rolling up a hill and emerging on the other side without ever having enough energy to reach the top. But superluminal tunneling added an extra layer of impossibility by suggesting this process could happen faster than light itself. The key to understanding this apparent paradox lies in the nature of wave packets and group velocity. When a wave packet encounters a barrier, something remarkable happens. Rather than the entire wave being transmitted or reflected, the packet undergoes a complex transformation. The barrier acts as a sort of filter, preferentially allowing certain frequency components to pass through while reflecting others. The wave that emerges on the other side is reconstructed from these transmitted components in a way that makes it appear to have traversed the barrier faster than light. This connects to two deeper physical concepts that help resolve the seeming impossibility. First, there's the distinction between phase velocity and group velocity. Phase velocity describes the propagation of individual wave peaks, while group velocity represents the speed at which the overall shape of the wave moves. In normal circumstances, group velocity carries the energy and information of the wave. However, in tunneling scenarios, the relationship between these velocities becomes complex and counterintuitive. The measured superluminal speeds refer to the peak of the transmitted wave packet, not the actual transfer of information. The second key concept involves quantum mechanical measurement and causality. Einstein's special relativity forbids information or energy from traveling faster than light, as this would violate causality, potentially allowing messages to be sent to the past. The resolution lies in understanding that what's being measured in superluminal tunneling isn't the actual transmission of information. The peak of the wave packet that emerges quickly was, in a sense, already present in the exponentially decaying wave function within the barrier. It's more accurate to say the barrier has selected and reshaped the wave rather than transmitted it at superluminal speed. This phenomenon has fascinating implications beyond pure physics. In optical communications, engineers have used similar principles to design devices that can reshape pulses of light, potentially increasing data transmission rates. The effect has also been observed in acoustic and electronic systems, suggesting it's a more universal wave phenomenon rather than a purely quantum mechanical effect. As you watch that strange commuter emerge through the wall, you might wonder if we've found a loophole in the universe's speed limit. But what we've really discovered is something more subtle and perhaps more fascinating. A reminder that when we probe the boundaries of physical law, nature often responds with solutions that are simultaneously more complex and more elegant than we might have imagined. The commuter hasn't violated physics. They've simply revealed that our intuitive understanding of through and faster might need some careful reconsideration. Rather like the delayed train in the tunnel, sometimes the most interesting physics happens not when we break the rules, but when we discover the rules were more intricate than we realized. Quantum phase space, you're trying to catch a squirrel. Not just any squirrel. This particular bushy-tailed menace has been raiding your bird feeder with surgical precision, always striking when you least expect it. But today, you've devised the perfect trap, accounting for every possible route of approach. Yet as you watch, the squirrel seems to take all routes simultaneously, existing in a cloud of probabilities that collapses into a single determined path only when it reaches your carefully placed nuts. Welcome to quantum phase space, where particles behave less like your typical garden pest and more like an infinite collection of all possible states until the moment of observation. In classical mechanics, developed by Newton and refined by Hamilton in the 1830s, phase space was a beautifully deterministic concept. For any particle, if you knew both its position and momentum at a given moment, you could plot its exact trajectory through space and time. This concept served as the foundation for centuries of physics, from celestial mechanics to steam engines. It was elegant, intuitive, and as Werner Heisenberg would later prove, fundamentally incomplete. The quantum revolution of the early 20th century shattered this comfortable predictability. Paul Dirac's landmark 1925 paper, The Fundamental Equations of Quantum Mechanics, introduced a radical new understanding of phase space. Instead of precise points representing position and momentum, quantum particles existed as probability distributions, described by wave functions that spread across all possible states. The mathematics behind this, developed through the work of John von Neumann and Hermann Weyl, revealed that quantum phase space operated under fundamentally different rules than its classical counterpart. The implications were staggering. Consider an electron orbiting an atomic nucleus. In classical phase space, it would trace a clear path, like a planet around a star. But in quantum phase space, the electron exists as a superposition of all possible positions and momenta simultaneously. This isn't just a limitation of measurement, it's a fundamental property of reality. The famous Heisenberg uncertainty principle, formally published in 1927, proved that it's impossible to simultaneously know both the precise position and momentum of a quantum particle. The more accurately you measure one, the more uncertain the other becomes. This peculiar behavior leads to fascinating phenomena that challenge our everyday intuition. Take quantum tunneling, first observed in alpha decay by George Gamow in 1928. In classical phase space, a particle confronting a barrier would either have enough energy to overcome it or bounce back. But in quantum phase space, there's always a non-zero probability that the particle will simply appear on the other side, having tunneled through the barrier. This isn't science fiction. It's the principle behind scanning tunneling microscopes and certain types of semiconductor devices. The rabbit hole goes deeper when we consider quantum entanglement. When particles become entangled, their quantum states are correlated in ways that classical phase space simply cannot accommodate. Einstein famously called this spooky action at a distance, but experiments have repeatedly confirmed its reality. The phase space of entangled particles must be considered as a single unified system, even if the particles are separated by vast distances. Modern applications of quantum phase space extend far beyond pure physics. In quantum computing, researchers manipulate quantum states to perform calculations impossible for classical computers. The field of quantum cryptography uses the fundamental uncertainties of quantum phase space to create unbreakable codes. Even in biology, there's growing evidence that quantum effects in phase space play a role in photosynthesis and bird navigation. Coming back to our squirrel, imagine if it could exploit quantum tunneling to bypass your defenses or exist in a superposition of states until the moment of nut acquisition. While macroscopic objects generally appear to follow classical rules, the quantum world beneath operates in a phase space of possibilities rather than certainties. This isn't just a mathematical construct or a philosophical puzzle. It's the deepest level of reality we've yet discovered, where probability clouds replace definite trajectories, and uncertainty isn't just a practical limitation, but a fundamental feature of nature itself. The next time you try to predict where that crafty squirrel might strike, remember that at the quantum level, nature itself operates on probabilities rather than certainties. Perhaps there's something oddly comforting in knowing that even the universe maintains a sense of mystery about its exact whereabouts. Panpsychic Particles. You're a quantum physicist working late in your lab when you notice something peculiar. Your coffee seems to be making decisions. Not big decisions, mind you, just tiny quantum ones. But there it is. Your morning brew apparently choosing which way its particles will spin, completely independent of measurement. At first, you assume you've simply had too much caffeine. But after weeks of careful observation, you're forced to consider a rather extraordinary possibility. Your coffee might be conscious. Not in any human way, of course, but at its most fundamental level, your flat white appears to possess some form of basic, particle-level awareness. This rather unsettling coffee conundrum leads us directly into one of the most fascinating and contentious ideas in modern physics, the concept of panpsychism at the quantum level. The notion that consciousness or experience might be a fundamental feature of physical reality, as basic to nature as mass or charge, has been gaining surprising traction in serious scientific circles, particularly through the work of physicist Sir Roger Penrose and his colleague Stuart Hameroff in their orchestrated objective reduction theory, published in Physics of Life Reviews in 2014. To understand why respected scientists are entertaining such an apparently outlandish idea, we need to grapple with what's known as the hard problem of consciousness, first formally described by philosopher David Chalmers in 1995. The hard problem asks how purely physical processes in our brains give rise to subjective experiences. The taste of coffee, the color red, the feeling of understanding quantum mechanics, or more commonly, not understanding it. Despite centuries of investigation and remarkable advances in neuroscience, we still have no clear mechanism for how consciousness emerges from matter. This is where quantum mechanics enters our metaphysical coffee shop. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, suggests that particles exist in multiple states simultaneously until they're observed or measured. This measurement problem has puzzled physicists for nearly a century. What exactly constitutes a measurement? And why should human observation have any special status in collapsing quantum possibilities into definite realities? Some theorists propose a rather radical solution. What if consciousness isn't limited to complex biological systems like brains, but is instead a fundamental feature of reality? Perhaps particles themselves possess some form of proto-consciousness or elementary experience. This wouldn't be anything like human consciousness, mind you. Your coffee cup isn't contemplating existence or planning to overthrow its human overlords. Rather, the suggestion is that particles might have some absolutely minimal form of subjective experience, an internal what it's like to be a particle. This idea gains particular intrigue when we consider quantum entanglement, where particles become correlated in such a way that the quantum state of each particle cannot be described independently. In 2022, researchers at MIT demonstrated entanglement between 8 photons simultaneously, showing how quantum effects can scale up in complex systems. If particles do possess some form of proto-consciousness, perhaps entanglement represents a kind of primitive sharing of experience, a quantum empathy, if you will. The implications of this perspective are rather staggering. If consciousness is fundamental rather than emergent, it would mean that everything in the universe, from electrons to elephants, possesses some degree of internal experience. Your morning coffee might not be plotting world domination, but its particles could be engaging in their own form of primitive experience, participating in the universal dance of quantum consciousness. This view also offers an intriguing approach to the combination problem in consciousness studies. How do simple conscious elements combine to create more complex consciousness? Perhaps quantum coherence and entanglement provide mechanisms for binding simple particle-level experiences into more complex forms of consciousness, eventually scaling up to human awareness through the precise quantum processes in our brain's microtubules, as suggested by Penrose and Hameroff. Of course, this remains highly speculative territory. Many scientists regard panpsychism as an unnecessary multiplication of entities, arguing that consciousness must emerge at higher levels of complexity rather than being fundamental. However, as physicist Max Planck noted in 1931, I regard consciousness as fundamental. I regard matter as derivative from consciousness. The debate continues in modern physics, with implications stretching far beyond your possibly contemplative coffee. So the next time you're working late in the lab, perhaps spare a thought for the quantum particles in your coffee cup. They might not be planning an escape, but they could be participating in the most fundamental form of experience in the universe. Then again, maybe you've just had too much caffeine. In quantum physics, as in consciousness studies, certainty remains elusive, but uncertainty has never been more fascinating. Topological light. You're brushing your teeth one morning, idly staring at the bathroom mirror, when you notice something peculiar about your reflection. The toothbrush in the mirror appears normal enough, but the light bouncing off its plastic handle seems to be knotted. You lean closer, toothpaste dripping unnoticed onto the counter as you observe what appears to be actual physical loops of light, twisting and braiding around each other like luminous strands of DNA. What you're witnessing isn't a hallucination brought on by too little sleep or too much coffee. It's a phenomenon called topological light, and it's every bit as strange as it appears. In 2016, a team at the University of Southampton created something that shouldn't exist: light that flows in knots. While we typically think of light as traveling in straight lines or simple waves, these researchers managed to create beams of light that twist and turn in three-dimensional space, forming stable structures that would make a sailor's knot-tying manual jealous. The breakthrough, published in Nature Physics, wasn't just a clever parlor trick. It represented a fundamental shift in our understanding of how light can behave. The key to understanding topological light lies in a branch of mathematics called topology, which concerns itself with properties that remain unchanged when an object is stretched, twisted, or deformed, but not torn. Topologists famously consider a coffee cup and a donut to be mathematically identical, as they both have exactly one hole. This same mathematical framework allows us to describe and create light fields with stable, unchanging features that persist even as the light propagates through space. These knotted light fields are created using precisely crafted holograms that shape both the intensity and phase of the light. The phase of a light wave is essentially its position in its cycle of oscillation, and by carefully controlling how these phases interact, scientists can create light beams that twist around each other in predictable patterns. It's rather like choreographing an extremely complex dance, where each photon knows exactly where it needs to be at every moment to maintain the overall structure. The implications of this discovery stretch far beyond making interesting patterns in laser labs. Topological light states are remarkably stable. They maintain their structure even in the presence of distortions or imperfections in the medium they're traveling through. This property makes them potentially valuable for everything from optical communications to quantum computing. Imagine sending data through fiber optic cables not as simple pulses of light, but as intricate knots that carry information in their very structure. The concept becomes even more fascinating when we consider its connections to other areas of physics. These light knots are remarkably similar to structures found in quantum field theory, particularly in the study of monopoles and other topological defects in fields. The mathematics that describes knotted light fields shares deep similarities with the equations that describe certain types of matter in extreme conditions, such as superfluids or certain exotic states of quantum matter. Sir Michael Berry's work on the geometric phase in quantum mechanics, published in 1984, laid much of the theoretical groundwork for understanding how these structures could exist. The Berry phase, as it came to be known, describes how quantum systems retain a memory of their evolution even after returning to their initial state, a concept that proves crucial in understanding how topological light maintains its structure as it propagates. As you finish brushing your teeth and wipe the toothpaste from the counter, you might wonder what other seemingly impossible things light might be capable of. The discovery of topological light serves as a reminder that even phenomena as familiar as light can still surprise us, hiding complex mathematical structures in plain sight. Perhaps the next time you catch an unusual reflection, you'll pause to consider whether you're seeing ordinary light or something a bit more knotted. Magnetic monopoles. You're holding the world's most powerful magnet, idly rolling it between your fingers while sitting in the pub, when something peculiar happens. The North Pole suddenly detaches and rolls across the table, leaving you with just a South Pole in your hand. Your friend Frederick watches it bounce off his pint glass with characteristic British composure, raising an eyebrow as the lone North Pole comes to rest next to the bar nuts. "Ah," he says, taking a measured sip of his ale. "I see you've discovered magnetic monopoles. Fascinating things. If they actually existed, that is." The hunt for magnetic monopoles represents one of physics' most intriguing, yet frustrating pursuits. You see, every magnet we've ever encountered has two inseparable poles, a north and a south. Cut a magnet in half, and you don't get a north pole and a south pole. You get two complete magnets, each with both poles. This peculiar fact was first systematically documented by William Gilbert in 1600 in his groundbreaking work, De Magnete. But it wasn't until the 19th century that its profound implications began to emerge. James Clerk Maxwell's electromagnetic equations, published in 1865, mathematically codified this two-pole nature of magnetism. Unlike electric charges, which can exist as isolated positive or negative charges, Maxwell's equations suggested that magnetic charges must always come in pairs. But here's where things get properly strange. In 1931, Paul Dirac demonstrated that the existence of magnetic monopoles would elegantly explain why electric charge is quantized, that is, why it always comes in discrete units rather than continuous amounts. His mathematical analysis showed that if just one magnetic monopole existed anywhere in the universe, it would explain why electrons all have exactly the same charge. The implications of this are rather staggering. Dirac's work suggested that magnetic monopoles must exist, or at least could exist, and their discovery would resolve multiple theoretical puzzles in physics. Modern theories, particularly grand unified theories, GUTs, developed in the 1970s, actually predict their existence. Some versions of string theory not only predict monopoles, but require them. The catch? We've never found one, despite decades of searching. Consider the peculiar nature of this quest. We're looking for something that would be relatively easy to identify. A particle carrying a single magnetic charge should leave a distinctive signature in our detectors. In 1975, we thought we'd found one when a team at the University of California, Berkeley, detected something that looked remarkably like a magnetic monopole. The physics community held its breath, but subsequent analysis revealed it to be a false alarm. Similar excitement arose in 1982 when Blas Cabrera's detector at Stanford recorded an event consistent with a magnetic monopole passing through it. Despite occurring on Valentine's Day, this potential discovery failed to blossom into a lasting relationship with reality. The absence of magnetic monopoles presents us with a delightful philosophical conundrum. How do we reconcile their theoretical necessity with their observational absence? Some physicists suggest they must exist, but are simply too massive to be created in our particle accelerators. Others propose they were produced in the early universe, but inflation, the rapid expansion of space shortly after the Big Bang, spread them so thin that finding one would be like looking for a specific grain of sand on all the beaches of Earth. The implications extend beyond mere particle physics. Magnetic monopoles, if they exist, would necessitate a revision of our understanding of electromagnetism. They would complete a beautiful symmetry in Maxwell's equations, making magnetic fields behave more like electric fields. This symmetry isn't just mathematically elegant, it would potentially allow for new types of technology, from novel forms of energy storage to more efficient particle accelerators. The search continues today, with experiments like MODAL at CERN, designed specifically to detect these elusive particles. Each null result simultaneously reinforces their absence and deepens the mystery of their theoretical necessity. It's rather like hosting an elaborate dinner party where the guest of honor never arrives, yet everyone's certain they must exist because their name is on all the place cards. As you watch that imaginary North Pole still spinning next to the bar nuts, consider that perhaps the most profound aspect of magnetic monopoles is what their pursuit reveals about the scientific process itself. Here we have a theoretical prediction so compelling that we've spent nearly a century searching for it, yet nature continues to withhold confirmation. It's a reminder that the universe isn't obligated to conform to our notions of elegance or symmetry, no matter how mathematically beautiful they might be. The pilot wave. You're having a perfectly normal morning swim, rhythmically gliding through the local pool's crystal clear water. As you surface between strokes, you notice something peculiar. Every other swimmer has vanished, leaving only their ripples dancing across the water's surface. These waves continue to move with purpose, guiding invisible swimmers through perfect lanes. In this moment, you've stumbled upon one of quantum mechanics' most elegant yet overlooked interpretations, the pilot wave theory, where particles surf through reality on invisible waves of possibility. In 1927, Louis de Broglie presented an extraordinary idea at the Fifth Solvay conference. What if quantum particles weren't inherently probabilistic, but rather guided by actual physical waves? His theory, known as de Broglie-Bohm theory or pilot wave theory, offered an alternative to the Copenhagen interpretation that had begun to dominate quantum physics. Published in his doctoral thesis, Research on the Theory of the Quanta, de Broglie proposed that particles always have definite positions and trajectories, choreographed by an actual physical wave that guides their movement through space. The mathematics behind pilot wave theory tells us something remarkable. Every particle in the universe is accompanied by its own wave, mathematically described by the same Schrödinger equation used in standard quantum mechanics. But unlike the Copenhagen interpretation, where the wave function is seen as a mathematical tool representing probability, pilot wave theory treats these waves as physical entities. The particle surfs this wave, following what's called the guiding equation, which determines its trajectory based on the wave's shape and intensity. This interpretation resolves many of quantum mechanics' most puzzling features. The famous double-slit experiment, where particles seem to interfere with themselves, becomes elegantly comprehensible. The pilot wave passes through both slits, creating an interference pattern in the physical wave field. The particle, while going through only one slit, is guided by this modified wave field to create the apparent wave-like behavior we observe. It's rather like a skilled surfer reading the ocean. They may only ride one wave, but their path is influenced by the entire pattern of interfering swells. The implications extend far beyond simple particle physics. Pilot wave theory suggests a fundamentally deterministic universe where quantum randomness emerges from our inability to measure the precise initial conditions of particles and their guiding waves. This connects to chaos theory in fascinating ways, like weather patterns emerging from countless tiny air currents. Quantum behavior might arise from the complex interactions of particles and their pilot waves. The theory also offers intriguing perspectives on quantum entanglement. Instead of spooky action at a distance, entangled particles might be connected by their overlapping pilot waves, creating correlations through entirely local mechanisms. Research at MIT has demonstrated pilot wave behavior in macroscopic systems. By vibrating a bath of silicon oil at just the right frequency, researchers created bouncing droplets that recreate quantum-like behavior. These walking droplets generate waves as they bounce, which then guide their motion, a perfect classical analog of de Broglie's pilot waves. The droplets even reproduce quantum tunneling and orbital quantization, suggesting that quantum phenomena might not be as divorced from classical physics as we once thought. Yet despite its intuitive appeal and experimental support, pilot wave theory remains relatively unexplored. The dominance of the Copenhagen interpretation, combined with the mathematical complexity of calculating pilot wave behavior for many particle systems, has kept it on the fringes of mainstream physics. But as computing power increases and our understanding of quantum systems deepens, pilot wave theory offers an increasingly appealing framework for understanding the quantum world. Back in your swimming pool, watching those empty lanes filled with purposeful ripples, you might wonder, are we all just particles surfing on cosmic waves of possibility? The pilot wave interpretation suggests that beneath the apparent randomness of quantum mechanics lies a deeper order, where particles dance to the rhythms of invisible waves that permeate all of space. Perhaps reality isn't built on probability clouds and observer effects, but on elegant mathematical waves guiding everything from electrons to galaxies through the cosmic dance of existence. Non-local causality. You're eating breakfast one morning when your toast suddenly pops up perfectly golden brown, and in that exact moment, your sister drops her coffee mug in Seattle. Nothing unusual about either event, except that her mug crashed to the floor precisely because your toast was done, at least according to quantum mechanics. The familiar cause and effect relationships we take for granted start to break down at the quantum level, where particles can influence each other instantaneously across vast distances, defying our comfortable notions of locality and causality. This peculiar phenomenon, known as non-local causality or quantum non-locality, was famously described by Einstein as spooky action at a distance in his 1935 paper, co-authored with Boris Podolsky and Nathan Rosen. The EPR paper, as it came to be known, attempted to demonstrate that quantum mechanics must be incomplete because it allowed for these seemingly impossible instantaneous connections between particles. Einstein believed there must be some hidden variables that would explain how particles could appear to influence each other faster than light could travel between them. But in 1964, physicist John Stuart Bell developed a theoretical framework that would eventually prove Einstein wrong. Bell's theorem showed that no local hidden variable theory could reproduce all the predictions of quantum mechanics. Through a series of inequalities, mathematical expressions that describe the maximum correlations possible between particles if they were governed by local hidden variables, Bell demonstrated that quantum mechanics predicted stronger correlations than could be explained by any local theory. The implications of Bell's work weren't just mathematical curiosities. In 1981, Alain Aspect and his team conducted groundbreaking experiments that tested Bell's inequalities using entangled photons. They measured the polarization states of pairs of photons separated by several meters and found correlations that violated Bell's inequalities, providing strong empirical evidence for non-local causality. These results have been repeated countless times since, with ever-increasing sophistication and distance between particles, including a 2018 experiment by Anton Zeilinger's group that used starlight from distant quasars to determine measurement settings, closing potential loopholes in earlier tests. But what does this actually mean for our understanding of reality? The most unsettling implication is that space itself might be an illusion, or at least not the fundamental backdrop for reality that we assumed it to be. When two particles are entangled, they exist in a state of quantum superposition where their properties are correlated regardless of the distance between them. Measure one particle, and you instantaneously know something about its partner, even if it's light years away. This isn't just a matter of revealing pre-existing properties. The act of measurement itself appears to determine the properties of both particles simultaneously. This leads us to even deeper waters regarding the nature of information and causality in our universe. If particles can influence each other instantaneously across any distance, what does this tell us about the speed of light as a cosmic speed limit? The answer lies in a subtle but crucial distinction. While quantum entanglement allows for instantaneous correlations, it cannot be used to transmit classical information faster than light. This is known as the no-signaling theorem, and it preserves Einstein's special relativity while still accommodating quantum weirdness. The phenomenon has practical applications too, forming the basis for quantum cryptography and quantum computing. Quantum key distribution protocols use entangled particles to generate secure encryption keys, with any eavesdropping attempt necessarily disturbing the quantum state and revealing the intrusion. Similarly, quantum computers exploit entanglement to perform certain calculations exponentially faster than classical computers, though building practical quantum computers remains a significant challenge. Perhaps the most profound implication of non-local causality is what it suggests about the fundamental interconnectedness of the universe. The physicist David Bohm proposed that our reality might be like a hologram, where every part contains information about the whole. In this view, the apparent separation between objects is an illusion. At a deeper level, everything is connected in what Bohm called the implicate order. So the next time your toast pops up perfectly done, perhaps you should ring your sister in Seattle. After all, in a universe where particles can influence each other instantaneously across any distance, who's to say your breakfast isn't somehow quantum entangled with her coffee mug? Though perhaps it's best to stick to more conventional explanations for household accidents, Occam's razor suggests that sometimes a dropped mug is just a dropped mug, even in a quantum universe. Cyclical dimensions. You're peacefully walking down a straight path when suddenly you find yourself approaching yourself from behind. This isn't a mirror, and you haven't turned around. You're genuinely seeing the back of your own head about 20 meters ahead. As you speed up in confusion, so does your doppelganger. If you slow down, they match your pace perfectly. The path continues straight ahead, yet somehow you're simultaneously in front of and behind yourself, locked in an infinite loop of self-following. This mind-bending scenario isn't just a thought experiment, it's a mathematically possible configuration in what we call a closed time-like curve, though in this case, we're dealing with its spatial cousin, a closed space-like curve. The concept emerges from Einstein's work on general relativity and has been expanded by modern physicists studying the geometry of space-time. In 1949, Kurt Gödel, yes, the same chap who turned mathematics upside down with his incompleteness theorems, discovered that Einstein's field equations allowed for solutions where space-time curves back on itself. While Gödel was primarily concerned with time loops, his work opened the door to understanding how space itself might exhibit similar properties. The mathematics behind cyclical dimensions reveals something rather extraordinary about the nature of space. Just as a paper strip can be twisted and connected to form a Möbius strip, creating a surface with only one side, space itself could theoretically be folded in higher dimensions to create closed loops. The key difference is that while a Möbius strip exists in our three-dimensional space, cyclical dimensions would require at least 4 spatial dimensions to exist without self-intersection. Modern string theory suggests our universe might have as many as 10 or 11 dimensions, most of them compactified, rolled up so tightly we can't perceive them. These extra dimensions aren't just mathematical curiosities. They're necessary for the consistency of certain physical theories. In 1926, Oscar Klein proposed that one of these extra dimensions might be circular, leading to what we now call Kaluza-Klein theory. What's particularly intriguing about cyclical dimensions is their potential impact on our understanding of fundamental forces. If certain dimensions are indeed circular, particles moving through space would exhibit wave-like properties naturally, a phenomenon that helps explain some aspects of quantum mechanics. It's rather like how an ant walking around a drinking straw might think it's moving in a straight line, while we can see it's actually going in circles. The implications of cyclical dimensions extend far beyond mere spatial curiosities. They might help explain why particles have the exact properties we observe. When a dimension is circular, only certain wavelengths can fit perfectly around the circle, similar to how only certain frequencies of vibration are possible on a guitar string. This mathematical constraint could explain why particles have specific masses and charges. These ideas have led to some rather remarkable theoretical possibilities. If space can loop back on itself in higher dimensions, we might need to reconsider what we mean by here and there. A particle might appear to be in 2 places at once simply because it's following a path through a cyclical dimension, rather like how a point on a ring appears to be in different places when viewed from different angles, despite never leaving the ring. The concept also raises profound questions about the nature of infinity. In a cyclical dimension, you could travel forever without reaching an end, yet the total space would be finite. It's rather like walking around the Earth. You could keep going indefinitely, but you're still confined to a finite surface area. This peculiar property might help explain why our universe appears infinite in some ways, yet could still have finite energy and matter. Some physicists have proposed that these cyclical dimensions might be detectable through careful measurements of gravitational effects. If gravity can leak into these extra dimensions, it would behave differently at very small scales. Several experiments are currently underway to test these predictions, though so far, no conclusive evidence has been found. As we return to our walking paradox, we can now see it in a new light. That strange loop you're trapped in might represent a path through a higher dimensional space that happens to curve back on itself. While we're unlikely to encounter such dramatic examples in our daily lives, the mathematics tells us that space itself might be far more intricate and interconnected than we typically imagine. The next time you walk down a straight path, perhaps spare a thought for the hidden dimensions that might be curled up around you, silently shaping the very nature of reality. Though you probably won't meet yourself coming the other way, The mere possibility that such configurations exist mathematically reminds us that the universe is far stranger than our everyday experience suggests. Quantum Darwinism. You're staring at your reflection in a coffee shop window, idly wondering if the you on the other side is wondering about you, when suddenly every passing car, every window pane, every puddle on the street starts reflecting you too. Not just reflecting, they're all measuring you, analyzing you, competing to capture the most stable version of your quantum state. Only the fittest observations survive, and before you know it, the entire universe has agreed on exactly who you are. This isn't some caffeine-induced hallucination. This is quantum Darwinism, and it might just explain how our classical reality emerges from the quantum realm. The concept of quantum Darwinism, introduced by Wojciech Zurek at Los Alamos National Laboratory in 2003, builds on the foundation of decoherence theory to tackle one of quantum mechanics' most persistent puzzles, the quantum to classical transition. While decoherence explains how quantum systems lose their delicate superpositions through interaction with their environment, quantum Darwinism goes further, describing how information about quantum systems gets broadcast and replicated throughout the environment, making it accessible to multiple observers. Think of it as a cosmic game of Chinese whispers, except instead of the message getting corrupted, it gets stronger. When a quantum system interacts with its environment, it doesn't just collapse into a classical state, it leaves copies of itself everywhere, like a celebrity whose every move is captured by countless paparazzi. But here's the crucial bit. Only the most robust, stable states get replicated successfully. These are what Zurek calls the pointer states, the quantum equivalent of evolutionary fit species. The mathematics behind this process, detailed in Zurek's 2009 paper Quantum Darwinism, Classical Reality, and the Randomness of Quantum Jumps, reveals something remarkable. The environment acts as both destroyer and preserver of quantum information. While it destroys quantum superpositions through decoherence, it simultaneously acts as an information channel, broadcasting select aspects of the quantum system to the wider universe. This broadcast isn't random. It follows a kind of natural selection process where only certain states survive and proliferate. But quantum Darwinism isn't just about information. It's about consensus reality. Consider this. When you and I look at the moon, how do we see the same thing? The traditional Copenhagen interpretation of quantum mechanics struggles with this question, but quantum Darwinism provides an elegant answer. The moon's quantum state has been copied and distributed so widely throughout the environment that we're all accessing the same replicated information. It's as if reality itself is a democracy, where the most widely agreed upon version becomes our classical reality. The implications of this theory stretch far beyond physics. In 2019, researchers at the University of Turin demonstrated quantum Darwinism experimentally using photons, showing how quantum information indeed gets copied and distributed in exactly the way Zurek predicted. But more fascinating is what this tells us about the nature of reality itself. Our classical world, with all its apparent solidity and certainty, might be the result of a cosmic consensus-building process, where quantum possibilities compete for survival, and only the fittest become real. Consider the philosophical ramifications. If reality, as we know it, emerges through this process of natural selection at the quantum level, what does this say about objectivity, about truth? The parallel with biological evolution is striking. Just as the species we see today represent the survivors of billions of years of natural selection, the classical reality we observe might be the survivor of an ongoing quantum selection process. This brings us full circle to that reflection you were pondering in the coffee shop window. Perhaps you weren't just seeing yourself, you were witnessing one of countless copies of your quantum information, all part of the universal broadcast that makes you classically real. In a universe governed by quantum Darwinism, every reflection, every measurement, every observation is part of an endless process of selection and replication, turning the quantum soup of possibility into the solid reality we call home. And if that makes your head spin, take comfort in knowing that somewhere, in countless tiny quantum interactions, the universe is busily making copies of this very moment, ensuring that the confusion you're feeling right now becomes an objectively real part of our classical world. After all, in the game of quantum Darwinism, confusion about quantum Darwinism is just another state competing for survival. The Quantum Bayesian. You're standing in front of two identical doors in a pristine white laboratory. Through one of them, a cat is definitely alive. Through the other, it's definitely dead. A physicist hands you a sealed envelope containing the results of a quantum measurement and tells you it will determine which door you must open. But here's the twist. Until you open that envelope, both cats exist in a superposition of states, and your knowledge of which door leads to which outcome quite literally shapes reality itself. This isn't just another thought experiment. This is the world of cubism, where quantum mechanics isn't about particles or waves, but about what we can know and how that knowledge shapes the physical world. Cubism, or Quantum Bayesianism, emerged in the early 2000s through the work of Carlton Caves, Christopher Fuchs, and Rudiger Schack. It takes its name from Bayesian probability theory, developed by 18th century mathematician Thomas Bayes, but applies these ideas to quantum mechanics in a radical way. Rather than treating quantum states as objective features of reality, cubism suggests they're expressions of an observer's knowledge and beliefs. The mathematics hasn't changed. We're still using the same quantum mechanical equations developed by Schrödinger, Heisenberg, and others. But cubism reinterprets what these equations mean. When we write down a quantum state, we're not describing some mysterious physical reality. We're describing our state of knowledge about what might happen when we interact with a system. This might sound like we're simply saying quantum mechanics is all in our heads, but that's not quite right. Take our two-door cat scenario. In traditional interpretations, we might say the cats are in some bizarre physical superposition until observed. In cubism, there's no weird physical state. Instead, the quantum mathematics describes our uncertainty about what we'll find when we open a door. The cats are definitely either alive or dead, but our knowledge, expressed through quantum mechanics, shapes how reality unfolds for us. This brings us to one of cubism's most profound implications. In most interpretations of quantum mechanics, measurement is this mysterious process that collapses wave functions and creates reality. But in cubism, measurements are simply experiences, moments when an observer updates their knowledge about the world. That sealed envelope isn't causing any spooky collapse. Opening it just updates what you know about which door leads where. The parallels to Bayesian probability are striking. Bayesian statistics treats probability not as an objective frequency of events, but as a degree of belief that gets updated with new information. Similarly, cubism treats quantum states not as objective features of reality, but as degrees of belief about possible experiences. This interpretation solves some of quantum mechanics' most notorious puzzles. The measurement problem? Gone. Measurement is just learning. Schrödinger's cat? Simply an expression of uncertainty. Quantum entanglement? A correlation in our knowledge about possible experiences. Even quantum randomness takes on a new light. It's not that nature is fundamentally random, but that there are fundamental limits to how much we can know about future experiences. But cubism isn't without its critics. Einstein famously said that God doesn't play dice with the universe, and many physicists today would say that cubism goes too far in the opposite direction, making quantum mechanics too subjective. If quantum states are just expressions of knowledge, what are they knowledge of? What is the underlying reality? Cubists have a surprising answer. They suggest we've been asking the wrong question. Physical theories aren't meant to tell us what reality is. They're tools for making sense of our experiences and predicting future ones. The success of quantum mechanics isn't in revealing some ultimate truth about reality, but in providing an incredibly accurate framework for understanding how our actions lead to experiences. Coming back to our two doors, cubism tells us something profound. The quantum state isn't some mysterious physical thing floating between the doors. It's your knowledge about what you might experience when you open one. The mathematics of quantum mechanics isn't describing some weird quantum realm. It's describing the optimal way to update your beliefs when you interact with the world. This interpretation reveals something beautiful about the relationship between observers and the physical world. We're not passive spectators in a predetermined universe. We're participants in a reality that unfolds through our interactions with it. Our knowledge, our actions, and our experiences are fundamental to how the world manifests itself. The next time you find yourself puzzling over quantum mechanics, remember those two doors. Perhaps the strange mathematics isn't describing some incomprehensible quantum realm. Perhaps it's describing something far more intimate. The relationship between what we can know and what we can experience.